Try now. Sorry, we're having issues on our end.
Yeah, we talked about slot time.
5 minutes to five. Yeah, it's the MIT 5. That's what we call it. Yeah. So that is part of the official timeline.
I think we're good to go.
We're good to go?
Yeah.
Is the audio on the owl right now or on the computer?
Let's see.
Where's the mic?
My mic is off.
The owl.
Yeah, I should bring that. The owls. Here. Okay, great. Sweet. Okay, awesome. Should we start the recording?
Yeah.
Okay, great. All right, everyone. So it is hard to believe, but it's April 19th or 29th, sorry. We have 2 more weeks left of the semester, basically. There's today's class, next week's class, and then it's your final presentations. So I don't know where this fall semester went, but it is almost gone. It's crazy. And very, very excited for this last kind of sprint to the end. And also very, very excited for all of your final projects and all the work that's happening there. So we're going to do a couple things today. We're going to kick off with, as always, with our homework review. So grateful again to Lindsay, Ashley, and the entire Waters crew that is back here again with us. So we'll thank them in a moment and dive into the homework. But we'll do that for at least 45 minutes. We'll spend a little bit of time on final projects. So just as some quick updates, your orders are all, again, being processed and arriving fast and furious, hopefully. So I think Twist Agene should be arriving.
Agene's arriving Monday.
Monday.
Yeah.
Monday. Today's Tuesday.
Next Monday.
Next Monday.
Yeah.
Okay.
So May 2nd. Actually, May 2nd is Friday, right? So this week, yeah.
This week. Okay,
Sooner.
that's good. Great. And then the twist orders are.
Twist orders are arriving on a daily basis. So like there's some right here. We'll
there you go.
as we go.
Okay, amazing.
Heard them so far?
So you will message them.
Yep.
Okay.
Yeah, Ronan and I will do that.
Okay, fantastic. Yeah. And so we'll spend a little bit of time, I mentioned this in my email out to everybody over the weekend, but we would love to hear your experimental plans in terms of what you're doing with this DNA out of the packaging. How are you going to start working with it? Where are you going to start working with it? What are you going to do right away? And also, again, I think there's a key part that we're going to focus on this week is your final project presentations. Okay, so this recitation on Wednesday, it's going to be all about your final projects, all about your presentations. We're going to show you in gory detail, like the key parts and elements that you need to have in your presentations, and then give you time also to work with some of the TAs to then think about that for your own project. Okay, so that's a lot of what Wednesday is going to be about. And then today, we have joining us from Stanford, Professor Manu Prakash. Manu actually was a grad student at the Media Lab many moons ago and has since gone on to do great things. He's won a MacArthur and launched this whole field called frugal science, which we're going to learn about grassroots biotech out in the field. After Manu's talk, in whatever time remains, I'll give a talk about continuing on the theme of tools. Around microfluidics, which some of you I know are interested in. So it's another set of biotechnologies that are about automation and programmability. And then a little bit about the microbiome. So we've been talking a lot about different types of single-celled organisms, and we'll conclude today talking about communities of organisms. So that is basically our agenda. And any questions so far about anything? Everybody okay with this plan? Yes? You guys give me some good eye contact, like look up from your computers and just look at me for a second. All right, there we go. Great, thank you. Eye contact is very, very important. Lets us know that you're here, paying attention. All right, so why don't we shift gears and go into our homework review. So again, so grateful to Nathan, Ashley, and Lindsay, and the entire team. And actually, if we don't give a big round of applause and thank you to Waters. So blown away by all of the effort and all the great work on your side in preparing everything. And we'd love now to hear about your experiences and how the homework went. Okay, so I know Ronan gave it a shot, took about 5 hours to do. I'm curious to hear all of your experiences. So again, we'll open it up. So if anybody is proud and feels courage and wants to share, feel free to do that. We would love to, again, and remember, I always remind you guys this, but third year grade is about attendance and participation. So we do actually track when you guys raise your hands and do things. So if anybody wants to share how the homework went, both good and bad, and your experiences in the lab last week, we'd love to see that. So we'll open that up if anybody wants to volunteer. Otherwise, we can always
And the love
the wheel. Yeah, we always go to the wheel, the wheel of doom or joy. Anybody feeling the call? All right, nobody's feeling the call. Then Susan.
Actually, you want to do it?
Oh yeah, totally. We get to do this every week. This is
It's not the most up-to-date list, but
yeah. We'll see if they call. Yeah,
It's exciting.
I know. It's really. I mean, for us, it's exciting. For them, it's probably terrifying. But it's Esther. The wheel has called you.
First try.
The wheel has called you, Esther. Come on up, Esther.
Great.
Come on up, Esther. Yes, yes.
you also post all the pictures too in the Slack, so it's great. It's great. You have to-
Excellent. This is excellent.
And again, so just for the water slopes, Esther is a designer by training, and this biology is new to Esther. So
Yeah,
this is,
Thank you.
well, no, but it's an amazing story. I mean,
Yeah.
everything you're doing, it's crazy. It's the most the largest chasm of in terms of background into what you're doing now. So I think it's always really great to see your work and your progress. So
Oh wait, why is it too easy here? So at the lab, Shrika and I kind of prepared a sample, the EGFP and the denature EGFP for the LCN MS analysis, just to compare them. And we centrifuged the two biored microns biofilm spin column for 2 minutes at the 100 RCF, I believe, just to remove the plaquing buffer and repeat it for three times. And then we put the denature and the native EGFP into on the top of the spin column and did the centrifuge for 2 minutes and 2000s. And then after that, we syringe into the machines and got this awesome graphs. And then we calculated, and these are the numbers that we got after the calculations. And yeah, you saw the whole process.
so just
Facilitated.
Yeah,
Esther, say a little bit more about the graph here.
the graph, yeah.
Or I guess what is the what generated the graph? What process did you go through to get this graph? Like I know you just gave a few experimental steps, but then what is what's going on in your understanding of how we got here?
I think we have to choose two picks and then we.
Choose two what?
Two picks. and
Yes, that's the
three-
decompose.
Oh, two peaks. Yeah. That's right. Okay, good, very good, great. I see a lot of math over here on the
Yeah.
right. Okay, sounds good.
Sure, it can help you a lot with that process.
Good. Fear-based learning. That's what it's all
Yeah.
about.
Here's the way of saying if the math is wrong. Isn't it?
I believe her, so that's the whole process that I did. And for the other steps. Sorry. No, it's not moving.
Actually, was there. What do you-
Oh, I need to scroll down and cover. Oh,
There you go. Yeah.
and this was the all that we did together. So for the other data, I used the data that we given.
Mhm.
So this one, I redid it with the numbers that we were having. So I found the picks from this paper that choose to like N 966 and N plus 1000 and calculate it based on the equation that we're given.
Wait, and sorry, so what was your result? You got your math accuracy. Let's talk with Lindsay a little bit about
Should we?
what this means. Yeah.
Okay. Yeah. There are some gotchas in there.
I might be wrong. So
It's okay.
yeah.
It's okay. So talk me through your process there.
So I firstly choose one picks from this graph. Which one is the 966?
Can I point out the wrong?
Yeah.
Okay. So you guys remember from the class, as we move to the left, the charge goes up or down?
Up.
Up. So first thing here, first peak, right,
Yeah.
is gonna be, this is the N plus one,
Yeah.
this is gonna be the N.
Yeah.
Actually, I think you do have it right here, you just have it maybe run upward, but I think you have it backwards maybe here.
Oh, okay.
So like you sort of got it and you sort of flipped it at the same time, which Is it too bad?
Okay, okay.
Yeah. So this is actually the easier part, believe it or not. I'm gonna have you go up. As you calculated the experiment or the theoretical first, right? Now, what did everyone get for their theoretical molecular weights? Let me rephrase this. Did anybody get less than 50 ppm mass accuracy? Not a one. I didn't expect so. That's okay. I don't grade your homework. I don't know the TAs do, so they can figure that part out. So let's go to your experimental calculation. It's good. It's the 28 charges multiplied by 28. That's all good.
Okay.
Except for the math doesn't come up with the number that I expected it to, so I don't know what it is. So I wonder if I'll put it somewhere. Let's see.
Is it?
Oh. Do you want to also involve the mark too, with the questions?
Yeah. How to do? I don't know how to. Should I just share? I don't know how to do this with
Yeah,
multiple.
you can share it, yep. And
Okay,
then they'll should override it.
Yeah.
They just
and then we'll
access-
come back to the peptide stuff. Which I think you guys will actually find was easier. All right. So. Did everybody use Xpesi to calculate their molecular weights? Now, the molecular weight that I got to using the sequence that we had in the homework
Mhm.
is 28,006.6. Now, the reason you get to that is the addition of the N-terminal methionine. Do you guys remember talking about that in the lab section? The cells are squirting out protein at such a high rate that it's no longer getting clipped on its way out. So while we might expect the protein to have that N-terminal valine, in fact, we keep the initiator methionine on there, or it kept it on there. And so we see this little bit of an addition. So that's the first tricky piece.
Mhm.
Did anybody get to that molecular weight? Close?
27,800 something.
Close?
875?
Yeah.
How much does methionine weigh? Does anyone know?
Vincent.
Well, it's 2,800. 3,000 minus 7,000.
Oh, about 130-ish?
Yeah,
Yeah.
That's it.
Anyways,
that tracks.
pretty close.
So that gets us close. Now there, in the recitation, you will briefly remember that I talked a little bit about the weirdness of GFP and how it forms its own fluorophore from itself, basically. Now, has anyone in the class taken organic chemistry? All right,
Long time ago.
couple of you will understand what's happening on the screen now. So it undergoes a cyclization reaction and expels a water molecule, and then undergoes an oxidation reaction and expels 2 additional hydrogens. So it actually loses 20 Daltons. It's a kind of tricky example, but a really good illustrative example of what happens all the time, because we have to look for the protein that we're thinking about. Weird stuff within the cell happens and we keep a methionine on it. And then we also have to think about PTMs, which this is. So to get to the correct molecular weight, we have to, we'll compare against the mass accuracy, take that 28,006, whatever it was, and subtract 20. So that's simple. In my view, this is the hardest part, is the first part of that question. All right, next one. So now we have Z. So we actually used the same 2 peaks. So I congratulate you on that. I chose them randomly. So the equation that we use is the M over Z n plus 1 minus 1. So 966.0069 divided by 1,4947, 966.
The other day said Ronaldo because he was wearing a Messi jersey.
Can you mute that? Yeah, thank you.
So this gives us charge states of 28 and 29. So that's probably where yours went awry, is I think because you mixed up which one was which. So so the 966 peak is actually the 29 plus charge state. Now when we do our mathematics here, we get 28 times 1,000 minus 28, or 27,985.85. And we're going to compare that against the 29,986.6 that comes from that theoretical molecular weight with the subtraction of the 20. And that gets us to 27 ppm, which is as close to right as you're going to get in mass spectrometry at this level. Does that make sense? All right, Esther, I'll pass it back to you for the peptide stuff because you were doing a terrific job.
Let me just switch the screen share on this. Cool.
For the peptide work,
Yeah,
I was trying to find the I don't know what's
lysine.
lysine and arginines
Yeah.
from the EGFP, and using the like the benchling, I kind of it gave me a like separate grouping. Yeah,
That's very strange.
it's strange. And try to skills it the grouping.
Okay.
They find a K and R from this.
Okay. How many did you get?
So I got 20 K and R.
I think that's plus, I think it's 6.
Is it 6?
Yeah. Like,
Yeah, yeah, count it.
and it was like 20K.
6.
Is this 6 R? Oh, two.
Mhm.
Oh, okay.
We had one of our scientists do it in the lab, and that was also what she came up with.
Oh,
I
yeah.
was very happy that she highlighted them all for me, so I didn't have to. Good work.
Okay. Oh, and then I went to the website to get this result, and I got 18 peptides from this.
Okay.
These are the result that I got.
All right.
And I counted directly from the metadata, and I see around like 20 and 21.
It's about consistent with what the group has gotten. There are some that are difficult, right?
Yeah.
As you get to the little tiny bumps, do
Uh-huh.
those count? Do those not count?
Okay, so
Acceptable.
okay.
Is there like, because the same issue, like,
Yeah, I would.
you actually have, which like. what-
Yeah.
So I count shoulders, which I think you probably did. So I think I can pull from the slides later because Ashley did a really nice job of putting green checks on them. So like this, I would count as 2 peaks. It's even 3 because I think there's a third one. That counts as 2. That counts as 2. I count probably those little guys. You get into it.
Oh,
It's the true answer is probably somewhere between 20 and 30,
20 and 30. Okay.
depending on how intense you wanted to go. There's some things that are probably in there that are below the baseline as well. So there's probably even more than that. The trypsin will start to cleave itself, so you'll sometimes see little tiny bumps that are actually the trypsin at autocatalysis. Or autolysis. But yeah, you're doing great.
So I just found that this chromatogram is finds more peaks than the line tool.
Mhm.
And I did some magnet gain, like based on this calculation that I had on.
Oh, that's great.
So I find the spacing is around 1.5, which is the doubly charged. So the CV is 2, and I insert that in that, and I got this number.
Yep.
And I got this accuracy around like 1.1. I forgot to
Convert.
yeah convert it. So and I guess what we got from is about 88%. So I consider this number percent. Yeah. right.
Easy question.
Easy
right?
question. So
Yeah.
and this is all for my ISO, like the
Okay.
around like since it's 88%, I like that's
Yeah, you got there. Yeah.
Yeah.
You can usually count from the software, but you probably didn't have access to that, so that's good. That's good.
but
Yeah.
that's
That's all I got.
yeah.
Okay. All right, Esther, thank you so much.
Yeah.
Bye. All right, so why don't we do a couple more and get hear your journeys going through this? Or actually, Liz, is there anything you wanted to share?
I mean, I have a couple more slides that
Yeah.
I could do, but I don't
Yeah.
know that it's anything different than what Esther just showed. Or anything profound.
Well, why don't we let another student present and
I
then
think so.
yeah, great job, Esther. Great job. Anybody else would like to share how their experience went in the lab and their experience with the homework? Otherwise, we can go back to the wheel. All right, let's do it.
Sure.
Let's see what the wheel reveals.
Let me just go back to this.
Welcome to class.
What's this about?
You owe us all $5 now. So yeah.
Okay.
Yeah.
This week, but I can.
Do you want to? We're doing the homework review right now for the mass spec.
Okay.
Do you have anything to share, or do you want to?
Sure, but I can talk to you.
What did you do the lab last week? Or you in
Yes,
the lab?
I did the lab, but I didn't have time to document it like.
I see. Okay, well, I mean, do you want, yeah, you can share a little bit. Yeah, why don't you come up and share a little bit about your experience at least? Yeah. The wheel has called you, so you must heed the call. So you can come and share a little bit.
Okay, hello. I think it was such a nice experience. It was very it was very nice to see other facilities out of our like labs here. And I think like it was very nice that we were like separated in smaller groups and we have the chance to see like all the details of the process. But it was very I was in a group that we did the GFP digest.
Mhm.
So yeah, so my impression of that was that it was very interesting to see the sequence from the pipetting to the machine that we had there.
Mhm.
And also being able to see the results and the graphs, and to also understand what the graph meant.
Mhm.
So yeah, that's my takeout of that. Unfortunately, I don't have details to share, but it was such a great experience.
So when I
Uh,
interview people, I like to ask this question.
Yeah,
What did you like the least?
but they like the least.
Good question.
Okay, so I think I didn't like actually that we didn't have the chance to do everything in the lab because we were in different groups.
Mhm.
So we were able to see in detail what we were doing, but we didn't have the chance to see what the other people did.
I said,
So that was that we missed, and yeah. So that's my impression.
Okay, all right.
Um,
No, that sounds good. Oh, actually, sorry. I'd forgotten about this. This is in your homework as well, right? And Esther, actually, we should have asked you this as well, but we can do this quickly. I'd love to hear from everybody before the end of today. But we talked about asking you to identify a thing that you're measuring in your project.
Mhm.
That was actually one of the key questions in your homework was, what is something that you spent a whole week talking about measurement technologies and kind of extra bonus credit. If you are interested in using mass spec as a part of your final projects, I think that's something we're also very excited to hear and would potentially be able to support thanks to the great folks at Waters. So maybe just a quick question for you for your final project.
Mhm.
What is something that you're measuring that you're trying to quantify
In my final project?
yes.
Yes. So I am, yeah. So it's actually a good question. I was trying to, so before answering that, I want to mention that there's a specific tube, like a specific material that you have in waters
Mhm.
that you were actually working with biosensor before and like the biosensor of PFAS. So this was very relatable to my project because I'm using a biosensor to identify PFAS. So I think that what it would be possible for me to understand like what's the amount of PFAS that we can identify like using like our material or like the biosensor, how is it possible to activate the biosensor using like a specific amount of PFAS or
Mhm.
maybe
compare them.
Yeah,
sort of thing, yeah. Orthogonal measurements.
Mhm.
Yeah,
So that could be
no, I think that's great.
Mhm.
I think that's very possible.
Mhm.
I am not the PFAS expert, but I know that we do PFAS measurements
Yeah.
in that lab all the time.
yeah. So
Okay,
That's good.
sounds very good.
That's
All right,
very
great.
promising.
Thank you, Dan. Okay, appreciate you. Appreciate you. Okay, let's do another, or actually, did you wanna,
Yeah,
why don't you hop into your slides a little bit? Yeah.
let me pop up a couple last things.
And we'll actually do a rapid fire go around the room with everybody sharing something that you're gonna measure. So know that you all will have to share something in like
Mm,
15,
That's
20
good.
minutes. So you have a little time. Think about
Maybe more like 5, but we'll see how long this goes. All
Okay.
right, so we covered this guy. You can see the fine work of our young scientist who highlighted all of those. I thought that was lovely, 6 and 6. Skip down a couple. Those were the same. So now you can see all the little check boxes covering all the peaks that we kind of sort of believed are real peaks. Arbitrary, arbitrary. Looking at the delta between the two peaks, derive the charge, calculate the mass accuracy from that. Again, depending on how precise you measure out the mass of those hydrogens and the protons, you might get a slightly different ppm. So we calculated out to a 5.3. I think Esther might have had 8.3. That probably has to do with the difference in mass between a proton and a hydrogen. A proton lacks one of those electrons, and we can measure that difference. It's really, really tiny, but we're able to, and so that's where some of those differences will come from, or significant figures. So bingo, 88, nailed it. And then looking at the fragmentation of one of those peptides, we're able to confirm from the spectrum what that looks like, and we can see a bunch of these different fragment masses within that from the homework piece. You guys remember that? So if we look in here, we see different fragment ion masses, 122, 214, 388. If we go back in here, we can see 288, or sorry, 388, 242, et cetera, et cetera. All right. Did anybody do the bonus questions? I don't blame you. I wouldn't have been involved. Yeah. Mhm. It didn't come up right. Got it. That is because for the bonus, we're not looking at the amino acid differences. We're just looking at the charging based on structure. Or did you, or were you talking about this one? This one. Yeah, let's see here. So we should see something at 774. I probably could have annotated it a little bit better. And so you see something called a Y7 ion. 774. So there's at least a couple of good ones in there. We tend to see the C-terminal ions when we fragment because the basic residue that we cleave the trypsin with the trypsin is always basic. So C-terminal lysine, C-terminal arginine. So you tend to look for those. There should be a 903. Yeah. So this will be, so this is the N+2H. It's the N+1H. Look at the delta between those. Figure out what the next residue is. Look at the delta between those and look what the next residue is. Okay.
Actually, 1 peak between like 602.
And it just disappears. Yeah, so it's a good observation, actually. That happens from time to time. And so there is an art in identifying which fragments or which amino acids will cleave next to. There's a little bit of a preferability based on gas phase physics. So certain amino acids, like glycine in particular, they just don't fragment super well. So sometimes those fragments, they're usually there, but it probably isn't showing up in that kind of printout of the spectrum. So sometimes you kind of have to dig in, but no, that's a really, really good observation. Mhm. That happens too. The reason for that is complicated in this case, but sometimes your fragments will fragment upon themselves. And this little mass table is a little bit simplistic. So in reality, we look for a couple of other types of ions. The software just kind of knows how to do that. And sometimes if those little fragments will fragment to what we call like an A fragment, you wouldn't necessarily see it. So it's a failing of the lab and how the thing was set up rather than you. But good work. Okay. So let's look at this one, the native versus the denatured, right? So we see the two different spectra down here, the native on top, the denatured on the bottom, attributing the different charging patterns to the different structures that we have in solution, right? And then did anyone look at the charge state identification from the native spectra? So pretty straightforward, just like Esther did in the homework for the peptides, looking at the spacing between two adjacent isotopes. Here we see that they're just about 0.1, which tells us that this is plus 10 charge state. So Z is equal to 10. So very simple and fast when we can see isotopes. All right, one more slide. Ashley?
Sure.
Yeah.
Am I good here?
Yeah.
Of course, go for it.
All right. So for those of you, I guess maybe mostly online who haven't met me, my name is Ashley Blum. I'm the head of Armor's Cambridge site. So that's Water's Research and Innovation Lab. We are looking to kind of get more engagement with students in general. So whether that's over the summer or throughout the school year, we have a lot of different options because I'm basically making them up right now. So if you're interested in hanging out more with the scientists over at Immerse or even a little bit with me, we'd love to have you. So just in terms of application process, just shoot me an email, include your resume. Would love to understand what you want to get out of that experience. As you can see from the slide over here on the right-hand side, there are a lot of different opportunities that we can kind of shape for you based on your level of interest. So if it's more molecular biology, then we can kind of do that. If it's a little bit more like, hey, I'd like to hang out with Sloane, don't know why you want to do that, you can do more stuff with me. So lots of opportunities. We also have a virtual opportunity in terms of if you have AWS or LLM experience. So feel free to drop us a note. We'd love to kind of get to spend more time with you all.
So, yeah, for everybody online, I hope you're able to hear Ashley okay there. This is a really special opportunity to engage more closely. And this is for our whole global audience as well. Again, just so you all are aware, part of what happens is, because, we literally have students, everywhere on planet Earth, and many of them are sleeping right now because it's like the middle of the night in Asia. But during the week, actually, for everybody's awareness, if you all know, during the week, the nodes, if they're not awake with us, they will watch the videos and then do homeworks with their own cohort in their own time zone. And so they actually have all been doing this exact same homework. We did a little check-in yesterday and their homework reviews. And yeah, so there were some students at Japan who were like, we spent the whole weekend just doing mass spec and then we didn't sleep. So anyway, so everybody around the world is kind of grappling with this in different ways, but it's great to know again. So I'm hoping global students as well can reach out if they're excited and interested. Waters is a global company. You all have sites I know throughout the United States, also in London. And actually, London is actually one of the sites of one of our biggest nodes, Life Labs. So shout out to that crew. There's almost 100 students over there. So anyway, so there's a lot of opportunities to engage with Waters in general. And I think for us, what we would love to see, this is again flying the airplane while we build it. It's the first time we've done this whole kind of mass spec measurement module, and so we would love see mass spec more actively incorporated into both the larger kind of group projects we're working on and then your individual projects. So and so I know for the global students as well, we just put this out there for everybody. If there is a way that you want to bring mass spec into your projects, let us know. There may be some weird, interesting ways we can either get samples or, we'll give you a little bit creative about it depending on what's going on. So, but the first most important step is if there is a way in which proteomics connects to your project, message Suvin, Ronan, myself, or for the global students, engage with your node leaders. Let us know. I think this is we're very curious to see, what folks might want to do with these tools. And it is a very rare and special opportunity. It's hard for, cutting edge researchers at MIT, it's hard for them to use mass spec. So the fact that we have the capacity to do so with Waters is a really special privilege and a great opportunity. So that is that part. And maybe just to kind of bring this home a little bit, we'd love to go around and hear from each of you what are things you are interested in measuring, and also if there is a way that mass spec might play a role in your projects. Okay, so we can do this with slides, or if you want to just talk about it, we can also do it that way. So we can just also go around the room if that works for folks, and we can have folks share a little bit. But Ricky, why don't you go ahead and start? What is something that you want to measure as it relates to your project? At least one thing, ideally more. If you can, yeah. go
Yeah,
for it.
so I am designing a genetic circuit that will express tardigrade D subprotein in response to the presence of luteinizing hormone.
Mhm.
So the luteinizing hormone is also something I need to make the cells express, but that'll be in the membrane. And then the damage suppressor protein will be produced in response to different amounts of the ligand. So I
Mhm.
think I would look to see, am I getting the D protein appropriately once I give it the luteinizing hormone?
Yeah, absolutely, absolutely.
And so what are some of the specific things you're interested in measuring related to the protein itself?
Well, I think I could use a similar technique to what we did in the GMP lab
Hmm,
to see
great.
am I getting the protein that I was looking for in the first place.
Mhm, mhm. And then for your experiment, how are you planning on trying to express the protein?
As in,
So you're right now, you have a twist order, I'm presuming. You got some like DNA coming in.
yeah, we have an
Right.
ad gene order,
Oh, you have an adjuvant order. Perfect.
Uh-huh.
Okay, great, great.
and yeah, I have it all sort of laid out in the experimental plan, but my thought is one way to do it, I have an ad gene order for a plasmid that already includes the DSEP protein.
Great,
It has a constitutively expressed CMB promoter.
great.
I want to use a restriction enzyme digest to take that out and put in the inducible camp responsive element promoter.
Okay,
And then that will respond to activation of the LH receptor.
okay, got it. So you've got two different systems that you're gonna
Yeah,
try to test.
yeah.
Okay, okay, very cool. And then you're doing this in E. coli, or what are you, what's?
Right now we have the cells.
You're doing mammalian, okay.
But I have backup designs for doing this in E. coli.
Okay, 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 all right. Has your DNA arrived yet?
I don't think so, not yet.
I think it's been something.
Okay, okay, okay. All right, and so, sorry, just to harp on this, okay? You got 2 weeks left, all right? It's like, we literally this is it, this is the final stretch. The thing that you should not say to yourself is, my reagents haven't arrived yet, so there's nothing I can work on, all right? Do not put yourself into that trap, okay? There's so much for you to work on even without your materials arriving, and in particular, your project presentations, okay? Which is why we're gonna spend the whole recitation tomorrow going over that. One of the magic things we do in science, especially when we try to publish great papers, and this is something that actually Joe taught me, he's my advisor, you write the paper with the data that you want to get. Like, especially, we're doing tool builders, there's experiments you want to run. Here in How to Grow Almost Anything, this is very much about building, growing, engineering, right? Making stuff. So there's an actual desired thing you're trying to achieve with your experiment. So in a way, you can imagine what that data looks like. Like I'll tell you a story about this. I'm going to share about this more later in my talk, but part of my PhD thesis was making the first microfluidic gene synthesizer. It's the first time anybody used microfluidics, these lab-on-a-chip devices to synthesize a gene. And so nobody had done that before, but I knew what the data I wanted looked like. I knew what I was going for, what I was trying to achieve. And so Joe was like, you just write the whole paper as though you've got that data. And then when you get the data, you put the thing in and then you send it. And I was like, oh, that's a brilliant idea. So that's what I did. I wrote this beautiful paper. I put in the graph that I wanted to get for this gel that I wanted to get, showing this assembled gene. And then I worked for months and months and months and months until I finally got that result. So do not wait until you have your results and your experiments to go and work on your final presentations. Start that now. Start that tonight, tomorrow, whatever it is. Map out your 3 aims. Again, now you've got your experimental aim, which should be pretty sharp. Build out your other aims and then flesh out all of the elements of your presentation. And then as you're doing your experiments, put in the data into this kind of masterful presentation that you generated that's going to share your final completed work. Okay, so start that process now. And also as a reminder, again, Ronan and Stephen are going to go over this in gory detail tomorrow. If you go back to class number 1, the principles and practices homework, right? You need to do that for your final project as well. That's something you can start on right now, right? You can think about what are the, kind of ways in which we have to think about safety, security, governance, et cetera. Literally that homework question from class number 1, but applied to your final project. And many of you already kind of touched on it in that first week. So, you've got something there, but do not wait, okay? Do not sit on your hands and be like, oh, my stuff isn't here yet, so there's nothing for me to do, okay? Is that message received? You guys all got that? Okay, good, great. So Ricky, thank you for sharing your plan. And yeah, let's keep moving on. What is something that you would like to measure in your project?
So yeah, my project, because I'm designer trained, I'm looking for very straightforward visual output.
Yes.
And I'm specifically looking at biosensor that detects zinc.
Mhm.
And initially, I was really like, I guess I simplified the problem too much. I was thinking that if it's possible to like, for like different intensity of zinc, it would provide like different rates of output. But I don't think given like the time frame this is doable.
Well, so
At least for right now, yeah, sorry.
just actually one thing there. So remember the things you can do in this time frame, that's your aim one. Aim one is like stuff you can get done in 2 weeks that you can get like some initial data for or kind of design stuff for. So something like that, if you want to have kind of a more quantitative approach where you've got put that in your aim two.
Yeah.
Right? That so don't take it off the table.
Yeah.
Put it into your proposal and into your presentation. But that's stuff,
I
yeah.
just mention it because it's
Yeah.
still part of the measurement, I guess. That
Good,
isn't
good,
a-
good, great.
your
But
question.
include that in your presentation.
Yeah, but in terms of like this specific lab that I'm trying to do is I'm actually breaking down my biosensor into parts and test different parts if it has reactions and see if, so it's more like an on and off, like a binary switch kind of situation, like see if it would react or like have visual output.
Sorry, and what is the thing you're measuring the visual output? for?
Like the biosensor,
Oh.
the circuit, I guess.
Okay,
That's the
okay,
circuit.
okay. Okay, so it's a zinc detection
Yeah,
system?
yeah.
Okay, but what's detecting the zinc?
Sorry. You mean the specific,
Is the zinc is binding to something and then you're
Yeah.
getting an output?
yeah.
Well, what is it binding to?
Working on it.
Oh, that's okay.
I can, sorry, I need to pull out my brush.
It's okay. No worries, no worries. But you have a colorimetric output or fluorescence or
I am actually testing two because I'm interested, I'm primarily texting like Z because it doesn't need to a specific, like I don't need to put it on the UV light. But
okay,
if that doesn't work, I'm also testing GMP.
okay.
So
So you're doing colorimetric and fluorescence.
Yes,
Okay,
basically.
okay, okay,
Because I was warned that Lexi has a very high chance of failing.
okay, okay.
Um,
That's good. And just said, so this is also good. Actually, Ricky shared this as well. So just for all of you, this idea of like risk mitigation, like here's this main approach I'm going to try. Like you want to do something in mammalian cells. That's great. Also kind of hard. That doesn't work. In parallel, you're going to try this other approach using, non-mammalian cells, E. coli. Also great, right? So if you've got two different types of readout, a
Yeah.
colorimetric approach and a fluorescence approach, that's
Yeah.
great. So how about
Yeah.
but sharing that type of thinking is great, right? So if you've got multiple approaches and you say, hey, there are 3 ways that I want to measure this thing, but I'm only going to have time to do approach number 1, but there are these other 2 approaches that are part of my consideration. Share that with us. So that is all that I would say kind of gets into the thoughtfulness category of your work, right? We can see even if stuff arrives late, didn't work in the lab, we can see the kind of level of thoughtfulness that you've gone into your experimental plan.
That's
great.
The gradient stuff, you can actually show well plate and just get an increase in concentration and then some other amounts, and you can just show that very nicely visually. So I encourage people to do that if they want to test a bunch of different conditions.
Okay.
Just have a wall plate, draw different arrows. So
yeah, like,
That also is a great segue into the liquid handling, the open trons, right? Again, I'm not sure how many of you are planning on doing anything with the robots, but that's another key thing. Like in general for the projects, I think we've been saying it hopefully explicitly enough, but the point is to pull from as much as that you've been learning on from the class as possible. Bring in some robots, bring in some genetic circuits, bring in some cell-free system, bring in some mass spec. All of these things have been a part of your kind of toolkit of skills right now. So the more that you pull in from across the class, that for us I think is really, really exciting to see. So
the answer to that question.
yes, please go ahead.
BZNT8 and.
That's a protein?
Oh, the protein?
Yeah.
So the protein I'm choosing PUC19 as a backbone.
PUC19 is the backbone, but what's the gene?
Basically, I'm not sure if this is answering your question, but I'm designing the parts that would attach to the PUC19 backbone. So
Okay.
it's like a series. I'm not sure which one are you asking for.
I was just trying to understand more about the biosensor, but
Yeah.
that's okay. The question right now is more about the measurement, and that's
Okay.
fine. So if you're going to do colorimetric and fluorescence, that's good. Okay. But again, just to get to the next level of the detail on that, like
Yeah.
what's the colorimetric tool? What is the thing you're going to put it in? And so this is where, again, just for all of you as you're going into the detail of your experimental plan, like I want to encourage you all to think deeply about like where you're going to do this measurement, right? If you're doing a fluorescence measurement, what is the box that you're gonna use? Is it like a gel box? Is it a plate reader, right? Yeah. Oh, yeah, there you go. That's very helpful. Great. Okay, okay, good, perfect. Okay, good. So you're gonna do a self experiment. Okay, great. Okay, but just you know, for how you're gonna measure, right? What is the machine or the system that you're gonna use to do your self measurement? And is it a plate reader? You know, is it a gel box, right? Those are questions that this now is the time for you to be having those questions or the answers to those questions for yourself in the front of your mind, right? Because if you're gonna go into the lab, how are you gonna measure this thing? You need to know what is the box or the tool you're gonna use. So, okay, great, awesome, thank you. Let's go, yeah, go ahead.
So for mine, I'm going to measure, so I'm doing antibiotic resistance, I need to measure like the minimum inhibitory concentration.
Mhm.
So concentration of epsilon that the type will stop growing at. And
That what stops growing at?
the bacteria will stop growing at.
Okay,
And so I'm planning on giving the bacteria kanamycin and epsilon resistance. It's all about planning on kanamycin first to see if it has the gene or not. And then I'm also, so I gave it ampicillin resistance, and then I also gave it a gene to neutralize that ampicillin resistance. And so we want to see how effective that gene is going to work. So we're going to have a bunch of different plates or wells with different concentrations of ampicillin in it, and then we only do a time of production. They each be a different day, and then we're gonna run it in the 3600, and then we'll see which ones will at which concentration it will start growing at, and that's kind of like.
wait, so is this more like live dead? Like, do you see colonies? Sorry, are you counting colonies at the end of the day? Or are you doing an OD measurement, or what are you measuring? Are you measuring colonies, the number of colonies, or are you measuring?
That would probably be easier. So I couldn't do that instead. I thought I was thinking putting in 4600 and then just kind of see.
So that's a growth curve. So you want to measure the growth of the.
That's a liquid culture. So you want to be very careful when you're plating it then, because it's like the way you plate it is going to influence very well the content. So just.
And it's a reminder, what is this? So, because what is the high level of your project again?
So it's changed a little. There's like ampicillin and there's genes that produce enzymes to neutralize ampicillin. And so I made a gene to neutralize the neutralizer. So,
What's the bigger vision again on your project?
creating a gene to turn off antibiotic resistance. Just like, yeah.
Creating a gene to turn off antibiotic resistance. Okay. Okay. All right. Well, we'll come back to that in a little bit. I'm forgetting now like what the overall like what your kind of visionary aim is. Like, is your what's the sorry, just very quickly, what's the larger goal? Like, what's the vision of your project?
Turning off like beta lactamase or beta lactam antibiotic resistance. Kind of just like it changed a little bit since I presented last time, which is the whole lactose intolerance one.
Okay, yeah.
But now it's just
But what's the purpose? What's the like?
solve antibiotic resistance.
Okay.
Now it's focusing on like.
Okay, so this is sort of like it's like a health related application. This is more like public health, global health.
Yeah.
Okay, got it. Okay, all right. So you're trying to measure OD and or cell counts, right? Like, okay, all right, good. Great. Thank you. Okay. Yeah, Shrika, go ahead.
Yeah, so for my isn't anything too crazy. I'm just measuring, for context, I am varying the rapidism binding site of the GFP and measuring the fluorescence. So I'll probably just use like a plate reader. I think there was one in the lab. I think it was a, I forgot the brand they had, but I think it was like a T-can. I'll double check. We'll just use a plate reader to measure that. And then I guess in regards to, so like I had a little side quest this week. I wrote this, but I'm not sure if you guys are familiar with like Rainbow, like the package that like it takes in like raw, or it's been taking in raw like Agile like .ds data, but I was playing around with it to do .ch, which is like the Waters native, and then I was trying to automate like that peak calculation because like it gives you access to the deconvoluted like peaks and just like instead of doing like I hated doing the math, so I was like, can you just like I don't know, I feel like it could be a final question, but like the TLDR is that I was hoping to kind of take that raw data in, and then my project is more so like creating like closed feedback and stroke optimization. And so I was gonna take that raw data and put it into like the ultra symbol model, like one of the data standards,
Mhm.
and see if I could just standardize, because what I'm doing is feeding the data back in to optimize like the next run of the reference binding set. And so I guess the novelty isn't like what I'm measuring the fluorescence, but I was looking to, just playing around with the data to see if I could like do some cool stuff with that.
And you're doing a whole automation system, right?
Yeah.
That's your bigger project still, right? Okay, great. But ultimately fluorescence potentially with a
Yeah.
flavor. Okay.
Yeah.
Now, so what in general, right? It's good to know what you want to measure now, how you want to measure it, what tool you're going to use, know how to answer that question. If not right now, by tomorrow, right? This is like as a part of your whole experimental flow, very, very important for you to know where you're doing this work. What is the machine or system that actually is going to get you that measurement that you want? So, okay, great. Thank you.
Yes, so to express two enzymes that can sequentially different water toxin called nitrocysteine. And I'm using E. coli to produce the enzymes. In order to gene fragments from this, I'll be including two different fluorescence tabs at the end of each enzyme. So after doing the data simply and bacteria so that it expresses enzymes, I'll be doing fluorescence expression of these two enzymes. Ideally under as a sensible, we can order some the cleavage of the toxin using the enzymes. This should be able to be done in mass spec. See if the microsystems and whether it's being switched into the
Great. That's awesome. Yeah.
Yeah.
That's fantastic. Great. So one question, the first fluorescence measurement that you mentioned, so that was you're trying to for that part. So what you're describing later with the cleavage, that's your assay, right? That's how you actually want to verify that your enzyme is functioning the way that you want it to. The first part where you're actually measuring the fluorescence, what is that? What is that again? You're measuring the fluorescence of what?
tabs are so to confirm successful expression.
Got it. Okay, great. Oh, so you designed that into your construct.
Yes.
What kind of fluorescence tag? Yeah.
One is GFP and the other is
Okay. Okay, great. Great, very good. So I'm not sure. So,
the last one. So two, and I'm not sure if I actually get to that one, but we can do 2 weeks.
yeah. It's a lot to do, but okay, but that's a great plan. That's a great plan. Awesome. And then yeah, similarly, where do you want to do your fluorescence measurement? Probably in building 68 or yeah, okay, great. Okay, awesome. Thank you so much. Great, thank you for sharing. Vincent.
So I'm automating that's yeah, and I guess the management actually see the experiment was successful and then yeah, and the one at the end of the day is actually the protein or DNA that we take to achieve to get with the kind of seeing this sort of aspect
Are you still focusing on a learning, the learning goal?
to an extent, I'm unsure if that's what exactly. But I think instead, you're just looking at the process in your vertical and introducing that to optimization.
Okay, I mean, so just in general, I mean, I hope you stick with the learning goal, right? That's a great, that was a great vision that you had overall. So just for everybody, stick with it. Remember, your aim 3 is your big vision, right? Like that. I'm kind of probing a little bit to understand because it's like you want to, all of your projects should have like some visionary way that you hope to make an impact on the world, right? That's kind of what you want. And I think where your overall goal of like trying to create a platform for learning I think that's awesome. That's super, super great. So don't lose that. Make sure that that's a core part of your larger visionary aim. And if you're using robotics as a way to get there, I'll actually talk about this a little bit later. That's a huge part of, I think, what the future of learning is going to be. Is going to be engaging with automation and robotic systems. So I think you're on a great thread, so don't lose that thread. Specifically, though, as it relates to what you want to measure, if there is, a specific kind of protocol or a way that you want to use the Opentrons to do something cool, great. And there too, you mentioned a couple things. You talked a little bit about DNA, proteins. You also mentioned mass spec. Like, is there a specific kind of protocol you're trying to execute or run on the Opentrons, like a type of experiment, or? Okay.
Look at, what the idea of assembly look like, that we've seen versus
Okay. Okay.
the actual, ultimate result here, I guess would be.
Okay. Okay. So my questions for you would be then, what are you measuring? Like, is the Opentrons, like what's the measurement component of your project, right? Like if you like Gibson assembly as an example, right? How are you gonna test or look at the efficacy of that process for your Gibson?
I guess in my case, I was simply looking at the right? So once the Gibson assembly is done, we'll get the result in a.
But how are you gonna measure that?
We have a fluorescent protein. Yeah.
Okay.
We're using it for instance, protein.
Okay.
Seeing that.
But the Gibson is about building the DNA, right? So then you're gonna express the protein how? You're gonna do it in cells, cell-free. Okay.
Do you
Well-
also want to do Sanger sequencing on the Gibson assembly, like the plasmid, just to verify they're the correct thing? It might be outside the electrons, obviously, but.
Also, so that Susan's raising a really critical point, which is like if your goal is to express it in cells, we can't currently do transformation on Opentrons, right? Like you can do the liquid handling and you can do you can run the reaction to build the DNA that you want, but if you want to then you could do a cell-free reaction in the Opentrons, which I might encourage you to do. That actually would probably be one of the easier things to do. But then even there, though, if you're going to do your fluorescence readout, that's not going to happen in the Opentrons, right? Like there's no fluorescence. Yeah. So okay. Okay. Yeah. Got it. Yeah. So I think just be clear when you kind of draw a box around your system, like what are the things that are actually going to happen in the robot and what are the things that are happening outside the robot, right? In this case, your measurement's going to happen outside the robot, right? So, okay.
Yeah.
Okay, good. But again, same question for everybody, right? What is the box that you're going to use for the measurement? If it's a plate reader, like where's that plate reader, et cetera, right? You have to make sure that you know how to know where that tool is. And if you don't know where that tool is, we can help you figure that out, but make sure you've got a plan for that.
David, quick.
Yes.
Check 305.
Yes, we're good. So Manu has actually got a class that he's wrapping up. So he has another 15 minutes. So we actually have another 10 minutes here or so. And just to say too, for next week's homework review, all right, because this week there's no formal homework no standard lab. Again, we're in the home stretch, so your full focus is on your final projects. Next week, for the homework review hour, that 2 to 3 o'clock hour, all of you are going to give us a final project update. Okay, so all of you are going to come give like your first version presentation of your talk. Show us your 3 aims, show us where you are with your project, where you are with your experiment, what's working, what's not working, et cetera. And again, do not fall into this trap of, oh, my stuff isn't here yet, I didn't do anything this week, right? We want you to see the thoughtfulness of your thinking and your plan next week, no matter what. So anyway, so we'll continue going around the room right now, but if I don't get to you before in the next 9 minutes, know that you're going to have to present next week in full anyways. So, but let's keep going around. Yeah, go ahead.
Genetics are good. So 2 parts I was prepared for cortisol. GLP reported
Okay, great.
I need to measure I need to make sure that it's I don't know if you have the research that time does, but
Yeah, it's an overnight thing.
okay. to measure the fluorescence intensity. And so I'll do that using my meter. And then also, so I'm going to do that, the 600 for that.
Great. Awesome.
Again, just need to vary the like. Impact level.
Awesome. Great. That's fantastic. Great. And how's the biosensor work again?
So it's T7 cylinder.
So you're expecting to see the fluorescence modulate as a function of the increasing cortisol? Okay. Okay. That's the hope. Okay. Okay. All right. Great. Great. Sounds great. Joe, also feel free to chime in. Yeah, as we go. But okay, awesome. Thank you. Yeah, go ahead.
So my first goal is that I'm going to it's by detection of PFAS in building materials, specifically in bricks or something else. So I wanted like to provide it to marginalized communities that they're living close in data centers or like tech companies because they to this area. So my first goal is that I want to make the biosensor work and to express fluorescence to the GFP to work in the biosensor that and then because GFP is not very stable and I wanted like to to see because it's going to be like visible with human eye with more people. So my first goal is to make the biosensor work. The second one is to make it less with the common proteins, and then the third one is to embed in bricks or in construction material. So the first thing, like for the biosensor, I'm trying to reproduce actually a paper that I found. The biosensor is so using the A, and I have in this plasmid I have a GFP and also one liver sequence that actually identify the PFAS. Yeah, so yeah, I'll try to make it.
Okay.
So I did find the PFAS. That means that we're going to have like the GFP working, and if it works, then I'm going to try with a compound.
So, but your bigger vision for this is that this is going to be incorporated into a brick of so like the building will change color in the presence of as like an environmental detector or like
Yeah,
I see.
It's like nature. I don't know, responding to pollutants.
Okay. Okay. And so and so just the biosensor itself again, what's the PFAS detection mechanism?
So actually, there's a sequence. So looking with human liver, actually, identify as the ability to identify.
It binds to PFAS or
Yes. Yeah.
or degrades it or
There's a conformal change.
I don't know.
I think it's the latter. You want to just double check, because then like if you're expressing some sort of GFP type that only does it when you have the conformal change, like say it's a receptor or something, then that's maybe not receptor is the right word, but just definitely double check if you have something that's expressed because of that. Because then that's what you're like, if it works, that's like the actual output you can directly measure.
Upregulate or downregulate.
I'm not sure. I mean,
The concern is if it downregulates GFP, then you need to control that because the thing you're sensing PFAS might also just degrade itself. So it's either build a detector that GFP increases or the thing you're looking for. What's that?
yeah, it should you should be upregulating like in the presence of the thing you're looking for, you get more fluorescence, right? That's So I think if you're trying to reproduce as a part of your experimental, your first aim, something that's not a previously done biosensor, that's actually fine. That's great. You know, if you've got a existing model, but
Yeah, what is it? I know how they build the specific sequence, but I couldn't find the sequence, so we designed something else with Arnold.
Okay,
We'll see that works.
okay. So did you already put in a twist order? Like a, okay, okay, all right.
Yeah, it's a structural change. So it's like, it's got this circularly permuted GFP in the middle and a liver protein around it. And then when it binds to the PFAS, it creates a little bit more fluorescence.
So there should
So it is upregulated. It'll always glow a little bit, I think, but it will glow even more in the presence of PFAS, is my understanding.
So the answer to Joe's question is, yeah, it does upregulate, right? So,
Yeah.
yeah.
Okay. Okay. All right. Good. And again, so just I forget which one of your peer students said this as well, but you may also want to consider if there's because right now it sounds like your measurement is occurring at the biosensor level. You may want to think a little bit about if there's a measurement you can do before just to see if the thing even expresses, right? How do you even know that is there something that you can measure to know that you even made the appropriate biosensor even without it working, right? That's another key thing that would be good to fold in. All right, so we just have like 2 more minutes. Esther, you've already. You've done a great job today. I'm not gonna put you on the spot anymore. You did great. I'll go in the back actually. Yeah, Cyrus, do you want to give a little? What is something you're measuring in your system?
Yeah, so I'm creating a system in E. coli that expresses the sense by a specific digital message is affected. So that's the message encoded in DNA.
And then there's
Yeah. Yeah.
So basically, of course, the sense is being expressed. I'm not going to try to measure that. I'm going to just I'm creating a secondary design of GFP as the gene to be expressed. And it wants to do that group as well. So basically, measure GFP on a big and I'll give you some sense of a sense of an idea as to how well the toggle switches that I use to control the expression.
Yeah.
Issue is that, of course, the toggle switches are quite specific for each gene.
Mhm,
It's not a direct comparison, but at least it tells me something
Mhm,
about the mechanics of the circuit.
Okay. Okay.
I'm not planning to measure the set.
Good. Good. But that's good. But you can put that in your aim too. Make sure you document that put that in one of your subsequent aims. Okay, that's great. So it's 3:15. Manu is joining us right now. So why don't we pause now and take a break? Okay. So for those of you that did not go at the end, you all are going to go first next time. Okay. So and we'll have more time. So again, for homework, so Wednesday tomorrow, we're going to do deep dive and recitation on your final project presentations. Next week, you're going to give us an update on where you're at. Give us an update on your aims, your experimental plans, your project presentations, and then if you did not have a chance to share right now what you're going to measure, hopefully you can give that to us in greater detail next week at the start of class. Okay, so why don't we take a 10-minute break? And before that, we do that. Just one more big thank you again to all of our colleagues at Waters. Thank you guys so much. And remember Ashley's call. If you want to do anything with mass spec, a few of you raised your hands about that for your projects. Please let us know. It's such an exciting opportunity to be able to incorporate that into your experimental pipeline. So let us know. And thank you guys so much again. Appreciate you. All right, 10 minutes.
For your class.
I am teaching. Yeah. I'll catch you right after this. Yeah. David, can you hear me? Can you hear me? Yes.
Yeah, we can hear you.
Awesome.
So let me just unmute this and test. No, the volume output needs to go to this. Yeah, there you go.
Okay.
Okay.
Can we just do tech?
Yeah, Manu, can you hear us okay?
I can hear you guys great.
Perfect. We can hear you great now too. Manu, it is so good to see you, sir.
Good to see you.
Manu, I'm here with Joe as well. Joe is over here.
Hey, Joe. Yeah, I saw you just on the video. This is fantastic.
Great to see you, Manu.
You're outpacing me, Manu.
Oh,
You
it's I just got off a boat. That's my excuse. I was out at
Oh, wow.
sea for a month and
How long?
we usually go in the Pacific current, so we're often either 20 to 30 days.
Wow.
Wow.
Okay.
Wow. Well,
Um,
Manu, yeah, we're so glad you're here. Do you want to quickly before we start, because we're in a break right now, do you want to test your slides real quick? Just so we make sure you just make sure anything that you want to share works.
yes, that would actually be a good idea.
Let's just do a quick little test.
And okay, can you see my screen?
We can. Yeah, that's great. Actually, try to play the slide. Yeah, do a full screen. Yeah, that's great. Perfect. It looks awesome. Wonderful. All right, great. Hey, Ronan, do you want to get everybody in the hallway to come inside? Well, actually, we'll get started right now. Oh, Manu you were with Drew too, right? Were you guys in India together? Drew was telling me you guys. I was like, what are you? Because like we were in a Silomar for we were working together for a few weeks, and he was like, oh, I'm going to be in India for a while with Manu. Did you guys? How was that trip?
It was fantastic. It was good. Yeah, I think yeah, there's a couple of sites that I usually go to, and there are a couple of new sites that we went. So yeah, we spent, I would say maybe 5-6 days together, and including Holi, which was quite
Oh, that's so cool.
so it
That's
was
so wonderful.
yeah. I think it's
All right. Well, why don't we get started? And
Recording in progress.
get the recording going here. All right. So we are hugely honored to have joining us today from Stanford, Manu Prakash. But having Manu here, it's always a homecoming. Manu was a graduate student here at the Media Lab, and I had the honor and the pleasure of working with Manu for many years, and we were in the basement over across the way, building devices and, clogging vacuum pumps and all kinds of fun things. But Manu over the past many years has been really had a spectacular career at Stanford and has been pioneering a field of research called frugal science. And it's both research, it's the development of tools, but I think what I've always been so inspired by Manu about, it's tools and science, but bringing the lab to people everywhere, all around the world, and to the field, right? So, we often think about the concept of a lab as a physical space that you go to run experiments. Obviously, in our class, and I'll talk about this a little bit later, we're increasingly thinking about robotics and cloud labs, where maybe you're interacting with a lab and you're not even in the lab. But I think part of what's been amazing about watching Manu's research over the years is the way in which the lab is now so decentralized and in the hands of people that may not have thought about themselves as scientists and now are really doing impactful science that connects to global health, public health, and so many other spheres. So Manu, it is always such a pleasure to have you come back to us at the Media Lab. You are always forever Media Lab. So we're so grateful to you. And yeah, everybody, please join me in welcoming Manu Prakash.
So good to be here. I am teaching back to back today. So I think I was thinking quite a lot about it. A lot of what we do is written up. And so I want to really turn this into much more of a conversation and have people ask. I'll kind of put some placeholders in place and then just let's decide where we might want to go. How much time do we have, Dave?
We have another hour and a half for the end of class. I've got some material to present along a little bit, but it's really this is your primarily to focus on spending time with you. So the next hour is great, but really it's up to you.
I think why don't I plan to just share a few things for the next half hour, and then depending on people's interest, we will dive deeper in very specific things because I think much of the point of these lectures and these engagements, from my point of view, is the hope that leads to action and things that people change what they were doing.
Yeah.
And as people that build a lot of platforms, it would actually be very valuable if any of you are interested in using the platforms we're building. So the hope is that something changes in your actions beyond after this lecture. Okay, so step one is I just stepped off a boat, so I have to take you to that boat for a second. So I just spent 20 days at sea, and in the middle of the night, this is what it feels like. We hit some rough weather. And why am I showing this to you? I'm showing this to you that while we were hit by, I would say, 15-foot waves for that one day in the Pacific Ocean, simultaneously at this moment, I was collecting confocal microscopy data of an instrument that we've built that allows us to do microscopy at scale out at sea. And so kind of the analogy that I want to give and share is that most of the time we do, oh, you guys are not seeing the slide that I shared. Okay, oops. Let me see. I want to share the whole screen and not the individual applications. Is there a way to share my screen? Because I'll be jumping back and forth.
Yeah, it's a good question, Manu. There should be a way to do that.
I'll just that's a bummer. How
otherwise
okay, I'll just do this in a second now. So now you see something else. And
we're seeing the ocean right now. By the way, Manu, I crossed the Atlantic Ocean in a boat myself over 12 days this November. So
yes, so you understand the the joy and the threads
You
around.
must be wobbling right now if you just got off the boat yesterday. You're
That is, yeah, it's been 2 days, so
okay.
it's been okay for some time, but I am definitely in my mode of thinking about the ocean.
Great.
Okay, I think what we'll do is I want to spend a few minutes sharing the philosophical principle, but then dive right into the sets of tools. I'll give you certain sets of hints and ideas. And based on those sets of hints and ideas, you can drive it and take this conversation in any different direction that you want to take. So as a lab, we think quite a lot about science doesn't just happen in our physical labs. Science happens all around us. The living world by itself, a very, very, very small portion of it will ever be contained in what we usually end up defining as a lab to begin with. Our foray into this was we started studying parasites and a lot of global health problems, and we just started interacting with people. And in that process, we learned that there could be another way of doing science, which is while we get exposed to both new kinds of problems and new kinds of parasites and new kinds of puzzles, and we personally think about wanting to tackle them, build the sets of solutions. Simultaneously, we have a capacity to build tools and share those tools with communities that we have built and engaged partnerships with. And that leads to a different way of how science scales. So much of what I want to talk a little bit about is how to scale science and scientific thinking and actions based on science, driven by scientific tools being made much more broadly accessible. Many of the ideas of things that we work on, there is roughly, I would say, a dozen plus projects that we have released at this point. I will specifically focus on one thing today just because I want to sharpen in and dive in on certain technical threads around them. But here is sort of the list associated with the class of tools. We just updated our website. So if you go online on our lab site, you can find many different tools that we've scaled up. Many of them have now become companies and are set on, have an open source framework around still building for-profit companies on open source hardware. So that's something that I'm very happy to talk about in the context of the community. They can be divided into three specific pillars. One of the threads is really science education, which remains our core principle of how do we really bring biology and life science education to people. The second pillar is environmental monitoring. Some of that is driven by sets of challenges in the aquatic environment, mapping the aquatic environment. Some of that is driven by thinking a lot more about mosquito-borne diseases and vectors and insect surveillance. I'm surprised I'm not seeing my slides change on your screen, which is really puzzling. So when I do that, now the slide changes, but when I do that, now the slide did not change. Is that correct?
So Manu, this happens sometimes for me on Zoom as well. It's a little
All
annoying,
right.
but
What I'm going to
you
do
can
is I'm going to
present not in
operate
full
in a
screen.
yeah, let's do that.
Yeah, exactly. If you stay in here, it'll work. Yeah.
All
And
right.
just go down this way.
Yes. Okay. So much of what I described, so the third pillar is around health itself, which is very directly focused on global health. There's a lot of work that we've been doing on manufacturing of diagnostic devices that I'm happy to just mention one or two words around. That program is scaling massively now. Of course, we do a lot of work at the combination and intersection of diagnostics and imaging and AI, which I'll briefly mention. And then more recently, we've also gotten into manufacturing, really focused around large-scale products that I feel should have scaled long time ago. And that's focused, the first sets of spaces are in that space of menstrual pads. We are trying to replace cotton Cotton is an environmentally, I mean, much of the world, cotton economy has a very strange relationship with the environment in the sense it's a very water hungry plant. And very recently, we've been looking at, can we look at plant biodiversity to come up with a broader range of sustainable plants? And that's led us to agave and a new way of thinking about actually how to manufacture menstrual pads in a distributed manner. So that's another project that's scaling. There's a factory in Kenya that we are building right now that's starting to manufacture this. By the way, agave is the same plant that many of you have probably had tequila from. For the first time, we've been able to show a plant that grows with absolutely no water, just as a weed, has the capacity to make a product that competes with cotton 1-to-1. There's clever biology in the process. But again, these are much more industrial scale products that we're starting to make. Much of what I describe is published, so take a look at it. If you're interested, you can dive in. But let me just talk a little bit about frugal science briefly, and then I want to talk about automation in microscopy. So who can tell me what is this object? Anybody in the crowd? Do you recognize the object that we're looking at?
Is this an oven?
Also, folks online, anybody have an idea? The first microscope, camera. Yeah, these are some good. Camera and microscope.
What else?
Some of the guesses.
Anybody else? Anybody joining from India? It's a very important object for Indian history. Of course, it's a very important object for history of physics, but particularly, yeah. What comes to mind when you think about physics in India and old times, colonial times?
Bose condensate.
Bose condensate. You're close. You're close. Yeah. Who else? Who else comes to mind other than Bose? What are the top 5 people that changed the history of science in India? A very important person that you've all heard and talked about in your physics undergraduate classes.
Raman.
Raman, exactly. The instrument you're looking at is an instrument that Raman built at that time for 200 rupees. That's what is in his notes. That changed the world. He discovered the Raman effect with this instrument. It's an optical instrument that allowed him to actually first, and I'll talk about Raman quite a lot in the context of that was his picture of him building the instrument. Everything was built in India. All the experiments were done in India. He never left the country. He was very specific around the idea of talent is everywhere. And in fact, given the kind of capacity and support, it leads to remarkable things. Actually, going back to boats, the whole reason Raman worked on this idea was because he spent time on a boat and he was interested in thinking about why the ocean is blue. And I'll get back to that in a second for why the ocean is blue. But that question, simplicity of questions, and the sense of ingenuity that you can actually discover completely new phenomena, you can build completely new tools, and you can frankly build capabilities that have not been thought about with very little. So just to put this in perspective, the instrument that Raman used cost around $3 or so. Maybe inflation and you count, okay, $10 possibly at that time. And he discovered a phenomena of Raman effect that at that time and we use Raman effect in all kinds of ways and forms, which I'll tell you about, and a new Raman instrument that we have released that allows us to do now label-free detection. So following in the footsteps of Raman, label-free detection of antibiotic resistance in TB. So what's fascinating with this is with completely no labels, we're not just detecting a bacteria and a signature of a bacteria. We're actually detecting genetically what is potentially in this particular bug to see which drug it's going to be resistant to. So just hold on and just think a little bit about it as a capability. This is a home-built Raman system in which we are able to train this system to not only detect TB as a bacteria, but detect which drug it's going to be resistant to. And I'll let you think a little bit about it. How is that possible? And clearly, if some of you think about proteins and coats of proteins on surfaces, you'll realize that there is enough on the surface of these individual bacteria to actually be able to identify and detect. So kind of going back to I want to spend a few minutes on microscopy because I've spent all my life making microscopy tools. Very much like you, I used to be a user of microscopes, and something changed in me and something snapped. I explicitly remember as a child, we used to be given exams. And for exams, one of the exam questions used to be draw a microscope and label all its parts. And it sounds like a pretty relevant question. You should ask kids, label all the microscope parts. Except neither me nor my teacher nor the entire school had ever seen a microscope. And I visited last year and I was looking through the textbooks, and still the question is still there. And you were supposed to draw the microscope exactly in the orientation that you saw it in the book. So if you draw it in a slight different orientation, you didn't get the points. And it's kind of, grad school, I spent some time at MIT and sort of, we spent lots of time thinking about all kinds of tools. But when I left MIT, one of the things that I was left with is this idea that often enough we attribute capabilities to places, and that should not be that way. And why is it that still a billion people are taking that exam and still doing the same thing that I did 20, 30 years ago? And it's sort of, I'll use microscopy as an analogy, but one of the key things that I want to describe is from that point onward, I stopped buying microscopes. We make our microscopes. And I'll give you that as an analogy that any of you can, and started thinking a lot more about what does it mean for the revolution in biotechnology? What does it mean to actually engage in biology per se? What does it mean for our connection with nature to begin with? And this is it's a joke, but I asked ChatGPT, what are the most important tools in science? And I don't actually agree with this. It shows microscope as number 2. Frankly, mathematics should have been number 1, or at least number 2. But it's starting to rival with mathematics, which is kind of interesting. But all of us, the way we get introduced to microscopy and the current state of affairs is these black boxes. I'm sure many of you have used these black boxes. You think about all these exciting new techniques that are coming out. Every one of them costs $500,000. Every one of them you are then essentially tied into this cartridge sets of models. So one of the recent questions, we've dedicated our lives to thinking about microscopy, manufacturing, and access. But more recently, we have now also tailored this to completely directly compete with the world's best microscopes in the world, but all built in an open source framework. So what you're looking at is data sets arriving from instruments we call squids. This is not the superconducting squid. I just wrote an application to the NIH, and it was a 30-page application, and the only comment I got, it got rejected, saying that making superconducting microscopes that use superconducting junctions will be pretty hard to make cheap. And I was just devastated. That's the state and reality of our science. SQUID stands for simple quantitative blah, blah, blah microscopy. Has nothing to do with quantum effects. It's just a name because I like marine organisms. In fact, I spent 30 pages and I could not explain to this person that it has nothing to do with quantum effects. So shame on me. So the purpose of this chat and talk is I just want to share with you the breadth of tools. They're rapidly growing. The community is building. Of course, we did this with Foldscope a long time ago, so we're learning from a lot of principles that we learned in microscopy. But now robotics and automation meets microscopy in our world. So just to give you a flavor of microscopes, this is a foldscope. Show of hands, how many of you have used a foldscope? So I may or may not even talk about it. You can tell because I cannot see the hands, Dave, what percentage of people.
We've got
Hundreds and hundreds.
Okay, so
in the room though, you should tell us a little bit about it. I think it'd be good.
Maybe
You
I'll
can tell
say a little bit about it in the very end, actually. So this is,
Okay, great.
I would say, the largest microscopy community in the world, amateur microscopy community. There's roughly around 6 million people. That's happened over the last 10 years. So it's been a long time in the making. And maybe in the very end, I'll kind of, when I talk about science activism, I'll talk a little bit about that. Anyway, there's a new foldscope that's out. Now there are new lenses. The point of this is for a price point of $1 to $2, can you image a single bacteria? Now, this is the second community that we built, maybe I would say over the last 4 years. This is planktoscope, so less people might have heard about it. This brings a degree of automation. So now for a couple of $100, we can build an instrument that allows us to be in the middle of nowhere, take a little glass of water, pour that in. You can see there's a little tube here, a little fluidic channel, a simple pump, a Raspberry Pi, and an imaging core. It does classification and it gives you an entire repertoire of what was there in that aquatic environment, completely in an autonomous manner. And most of the time I want to spend about is around these instruments, which are squids, which now for tens of thousands of dollars, so between $5 to $10 to $20,000, we can now build completely autonomous robotic microscopes that start competing all the way from confocal microscopy to fluorescence to Raman, and allows us to really push the boundaries of what we are trying to do in making open access in microscopy. All the software, all the hardware is completely open. In fact, it's now become essentially a farm of instruments. So they have a couple of different robotic modules, and I'll mention a few sets of applications, but then dive in on one specific application and how it all got started. Like, why did we get into automation in microscopy to begin with? And that begins with this photograph. This is a photograph that I took in 2013, maybe 2012. I was in Uganda. We've been working in Tororo for some time. And we have been thinking for a long while about malaria diagnostics. So why am I talking about malaria? So first of all, it's important to understand, and I want to state that explicitly. The world has changed. In the last 3 months, the world has changed. You might ask how it might have changed, and in all of your worlds, you might have seen different sets of changes. But very specifically, if you think about the role of USAID, USAID used to run a very important program called President's Malaria Initiative. It was 30% of support that goes in malaria. Much of the RDTs are subsidized based on that. And all of that has gone and disappeared completely. And this is in the last 2 months. So if I was to go, I could show you, type in pmi.gov, and the fact that even a program that ran for 30 plus years now, the website doesn't exist. We have taken a stance somehow in this world, which is a very naive and in fact stupid stance, that we don't need to care about what happens around the world. And when I say we, I mean taxpayers, us as taxpayers. Malaria has been on the rise for the last 10 years. So I'll let you guess this in some sense of thinking about 2015, we had roughly around 200 million reported cases of malaria. And I'll let you guess, in 2024, how many cases do you think we had for malaria? 2015 or 2013, the number of cases was around 200,000, 200 million reported cases. So where do you think the number is now? I mean,
Want to
remember,
guess?
we're putting $3 to $4 billion in malaria alone, massive programs. Every country has malaria control programs. Everybody works very hard on malaria. Which way has it gone, up or down?
Up. Our guess
Up.
is up.
Exactly. So we're nearing somewhere around 260 million cases now. Nobody has a good reason for why malaria is on the rise. There are two or three really scary reasons that malaria is now on the rise. So first of all, what does the human picture of malaria look like? The reason I wanted to show you this photograph is I took this photograph. I didn't know. I was walking back from this family. I spent a ton of time with these kids. We were playing around. There's a pregnant mother on the back. But the realization for me was these kids are playing and literally sitting on a tombstone for their brothers and sisters. This is a very common, harsh reality of malaria-borne areas where people will bury their deer in front of the house so you don't forget. Uh, we have a field sites across now 11 countries. This is one of the field sites in Senegal. And what you're seeing is, this is Bandafassi. This is a malaria clinic. It'll get somewhere between 300 to 400 patients. It's a one-room hospital. There's a doctor that's sitting. He's also the lab technician. Right behind, there's the urgent care, tons of kids. And in fact, now if I go and take you, this is one of our field sites in Kalahandi, and I want to show you. And believe me, I'll come back to microscopy in a second. This is the reality of what happens in a field site. So you're visiting one of these sites with me. I am with Durga and Prem here, and they will operate 7 days a week, 10 hours a day. They're spending time doing microscopy. And in fact, the stain that they are using for malaria is actually the Gimsa stain, which was first described by Juan Gimsa in 1904. This is the WHO gold standard. And so if you were to do 10, 11 hour of microscopy per day, you can start realizing how difficult it can get. And some of the statistics around manual microscopy has been sometimes less than 50% sensitivity specificity because just it's very difficult. It's about searching for a needle in a haystack. Simultaneously, two other really strange things have happened. Of course, we're not meeting any of our malaria goals to begin with, but something very strange happened in malaria, which is a big concern. The gene that was chosen for the RDT, by the way, the RDT costs around $3 to $4 per test. So that by itself is not sustainable if you think about it. And primarily because of the charity models that were built, we have not been able to reduce the cost around those RDTs because there was money flowing. But there has been a strain that for the longest time has actually evaded the gene that was chosen as a non-essential gene. So now we have created resistance against a diagnostic test. The most widely used test currently has a resistance. And so this particular strain spreads across the world with no checks. Simultaneously, we have drug resistance. Artemisinin is our biggest frontline drug, and there is a drug resistance. And the third piece of the puzzle, which I don't have in this deck, is we have a new mosquito on the line. So actually, a quick question to you. How many of you believe that in United States we have and we harbor the mosquito that's completely capable of carrying and transmitting malaria? Yes, raise your hands, and no, you can keep your hands down. How many people believe that in the US we actually harbor a mosquito that still can transmit malaria? Okay, I see Helen's hand.
Yeah, we've got like a third of the class thinks yes.
Third of the class believes that. A third of that class is correct. An important aspect of this is mosquitoes. I would argue we don't actually know what mosquitoes live in the United States. Forget about knowing. We are blind to an entire ecosystem of where these sets of species are, the sets of dynamics, where they go, what sets of parasites they carry. Much of the funding for mosquito surveillance has been cut off long time ago. And there is a new mosquito that's on the line, that's Anopheles stephensi, that's now transmitted from India through the Horn of Africa and is spreading all across Africa right now. The strange part of this mosquito is it has the capacity to transmit malaria for the first time in urban areas. So imagine Lagos, a place with massive density, actually having malaria endemics, and that started to happen. The first sets of ones in urban areas were in Ethiopia, and now finally it spread across the country. So lots of reasons to worry about. And in that core, when this current thread has come about, it's really has been a very scary thing to think about. I just spoke to somebody at Africa CDC, and I've been talking to a lot of our partners. 6 to 9 months of supplies are in place, and we're going to fall short. Roughly what we need to do is around 500 million to 1 billion tests a year if we're going to keep malaria under check. And again, I'm talking about malaria very heavily. You can replace that word with any sets of infectious diseases. And if we let many of these sets of primary health centers collapse, you will not have any surveillance capacity for anything else, including Ebola, Lassa, or any of the other diseases that you might care about that have potential for global pandemics. So it's quite a scary situation. We have put ourselves in it by removing the kind of support, by not actually initiating actions in the past that enable and bring power to communities rather than being dependent on infrastructures that are outside. And, I have to say this, ironically, this has been a very strange moment for me because I live in San Francisco. And guess what? I go outside my house, and every other time I go out, I see a Waymo driving around. So I feel as a society, the degree of failure that I feel every time I see a Waymo, of course, as a technologist, I love it. How many, I mean, I'm assuming some of you have traveled in a Waymo. If not, you eventually will. And I find what a remarkable thing that as humans, if we put our mind to, that we can do. And so I want to give you this contrast. And this is sort of our start 8 years ago when we said, okay, this is not a technological challenge, it's a social challenge. So let's build the sets of tools that will enable us to do this. And the equivalence of completely automating AI-driven microscopy in primary health centers around the world. That's really what we started building. The first sets of tools were called Octopi, and I'll kind of share those with you very quickly, and then transition to tell you a lot more about the other sets of tools that we built. So early phase, this was Octopi 1.0. The tools evolved. The current tool kind of looks like this, and I'm just going to show you what it looks like in the field. Currently, we have around 6 field sites where we finished the validation studies. Now we are in usability studies. So this is exactly the same healthcare center in Bandafassi in Senegal, Senegal-Mali border that I had shown you, where a healthcare worker is now routinely using and testing this tool. I'll tell you what the tool looks like. Let's just watch this video. Everything that you're seeing in this video is actually real time. So I'm just going to play this. And I have this joke about, I'm calling this Finding Waldo, except Waldo is a parasite. Every half a second, the screen is changing, and you have hidden in that screen, that's roughly around 10,000 malaria parasites. And in real time, the machine is picking up individual malaria parasites, all completely autonomously. And again, it took us a while to build this, 7, 8 years of technical advances. Now, how can we even do this? This machine has a capacity between 3 to 5 minutes. We can image 2 to 3 million cells and essentially achieve for 10 parasites per microliter, we can achieve 100% sensitivity specificity. So the machine is processing samples faster than the stage can move. So the stage moves to a new location, it autofocuses, it's completely hands-free, but the compute is on a gaming processor, again, GPUs, that we are now capable of doing all the analysis. So first of all, how can we actually do this? There was a really fun scientific discovery that we made in this, which has to borrow from astronomy. The trick was, in astronomy, when you look at the stars, you actually don't see the shape of the stars. Stars don't have any shape. They actually have color. And the aha moment for us was to actually build dyes and molecules that will bind to DNA and RNA differently. And we discovered a spectral shift. So you can see a parasite here that has a specific tinge of a color, and you can see a platelet that has a different color because it's DAPI binding to the grooves of DNA and RNA slightly differently, giving rise to this 10 nanometer shift. And that shift is what essentially drives this capacity. Now, one of the fun things that often happens in projects and ideas, and I'll tell you where we're taking this, this is kind of what the instrument looks like. We started massively deploying them. Recruited around 25 institutions. We started shipping this tool, and something really strange happened in India, which kind of was a setback to us. We started getting data and pictures from India, and the data looked like this. And you can see it looks like crap. I can't identify any cells. I see a small portion in which I can see it's all an overlap. And then we asked our partners to share how were they making the slides, and this is how the slides were being made. So there's somebody sitting on the floor doing an assay. And I want you to remember, biology happens everywhere. Remember, this is in the middle of Assam in a jungle. That's where falciparum hides in India. And we had an epiphany realizing that, wait a second, we've built this remarkable tool, but if the first step, which is making the slides, I'm assuming some of you have made slides. For the last 100+ years, we've been making slides this way. You take 2 glass slides, you drop, and you smear. This looks very simple, but it's not. And everybody who has done this before knows that there is a particular angle and speed that you have to do it, and that gives rise to a smear. Now, that's roughly around 20 million blood cells that you've smeared. And we asked ourselves a question, most of you have seen this joke that some things are as boring as paint drying. This is quite literally paint drying, and we asked ourselves a question, how does paint dry? So this is how paint dries. And essentially, we model how does a colloidal mixture in a thin film, this is Landau-Levitch, classic thin film, viscous thin films. There is a given speed and a given angle at which you can get a monolayer of cells. And then, of course, this math is not helpful if we can't embody it in an object. And again, I'm just trying to show you the spirit of frugal science. That's a 17-cent syringe and a 2-cent air valve. And that makes me a continuous velocity motor. No electricity. You turn that into a 3D printed object. And we've now scaled this. There are tens of thousands of these. We've been shipping around the world to users. You can print it in your garage. And every single time as an object, this makes a perfect smear. 20 million cells available to you. Then you can do all kinds of things. Now you notice there is a particular thing. We're not making cartridges. We're not in the business of selling razor blades and razor and the blade model. The integrated, this is something that you can use for hundreds of thousands of cycles. We've tested that in the lab, and it makes this perfect smear every single time. A little bit of math, a little bit of clever engineering, completely 3D printed tool, completely open source, that now allows us to solve that problem. We solved that problem, we went back, and at this point now, the Octopi 2.0 paper is out, and you can actually see the performance itself. We have the capacity now to diagnose malaria in the middle of nowhere for 5 cents a test, which is just the cost of a glass slide. Now you might say, oh, that's interesting, but that's just still malaria. And something really interesting happened, and I'm going to skip this. There's a lot of work that we have done on the class of models in machine learning. There's a lot of usability work that we have done that allows people, what does the interface look like? How do we make more number of people actually start using this? So this is data sets now collected by the community. There's also a big partner network that we have built. That partner network spans around Africa, Latin America, and India. We're gearing towards imaging 1 million slides, but I could tell you whatever I want to tell you. I think it's much more important to hear sometimes for individuals. So I don't know some of you, if you speak French or Wolof, I'll let this play. I know what the translation of this is, but I'll let her say what a healthcare worker in Senegal had to say.
Plus efficace. Maa ngi si mu doon on nous apparaît. Pose des questions. Est-ce qui est mieux, est-ce que c'est mieux plus que. Effectivement, effectivement. Et c'est ça l'objectif. Voilà. L'objectif.
Okay, what she told us is you are 30 years too late. I have already lost my eyesight. And it was kind of a striking reminder because most of the healthcare workers and primary health workers around the world, one of the hardest challenges that they put and dedicate their lives to something. And at that same time, they don't feel empowered in some of the work that they actually do. And so she's been a huge support. And again, many of the community health workers that we've been training, we've been teaching workshops with NIH, sets of institute pastures, to start to also ingrain and build the capacity. But something really strange happened, which I want to share with you, because sometimes when you think about projects, you don't realize that projects have a life of their own. I got an email, a couple years ago, I would say 3 years or so ago, from a student in UBC that was from Nepal. And he had a doctor friend in Nepal, and he asked us a question. You've done this for malaria. Why can't we do this for sickle cell? And the reason he asked me that question is because he was in my frugal science class, and he was one of the students taking the class. I had no expertise in sickle cell anemia. I said, why don't you build a team? You run the clinical trial. We'll ship you the tools. And within 9 months came out this study that now can actually do all 4 types of sickling, essentially using this platform. All the annotation, all the clinical work, all the validation was done by the team in Nepal. Now, that's very important to understand, is that once you've built a platform, you have the capacity to introduce completely new class of capabilities on this platform, but engaged with the community. We've now done this similar analogy for TB in Africa. There is a program that's currently running on sexually transmitted diseases in Kenya. I already told you a little bit about ramen on this same platform. And the reason I'm spending so much time telling you all of this is for me, it's become this analogy to an app store for diagnostics. We now have the capacity for a hardware that we have submitted an FDA approval for. We've also commercialized this hardware. It's completely open source, but still we do manufacturing for this. With algorithms and clinical trials and validation built by community, if you have an app that does it better than me on malaria, for example, we will run your app on it. And the idea is to build this in the context of partnership and actually bring individuals that bring clinical expertise to the table. And for a primary health center, it becomes a capability to do diagnostics, which is not constrained by supply chains. So this is kind of a big program that's starting now. We have around 20 plus partners for 20 or so diseases. If you have a disease in mind and you're excited about the clinical side of that story, you should reach out. But something really strange happened along the way. When we were building this, groups at MIT started asking us. I'm not singling out MIT. Lots of groups at Stanford also asked us for these tools. We didn't build these tools for Stanford and MITs of the world. We thought that they have plenty money. They can spend their money wherever they want. I want to focus on community health work. But I'm a kind person and I decided to share. And so there's actually 10 or so units spread across Boston. I have 15 or so units in labs around the world, and people were using these tools in all kinds of things. In BSL-3 facility, they started realizing that, for $5,000 to $10,000, we can do completely automated microscopy with an AI engine. That's a big deal. And so that led to, we opened up the platform and that became Squid. Squid now is a modular platform, has 30 plus modules around all kinds of capabilities that you put together to build any kind of microscope that you want. We've built 30 or so kinds of microscopes, all the softwares, and I'm just going to share a few sets of applications associated with the squids. The power of this tool is there are modules that you can connect. There are software tools, completely open drivers, and we can now combine this with robotics and some amount of robotic pipetting to essentially choose your favorite assay. And we can completely automate the same. So what you're looking at, this is an OPS implementation running in our building. And one of the things is we've been mapping every possible, so spatial genomics kinds of applications where microscopy is the readout, implementing on these sets of platforms. And then I'll give you example of a few sets of applications per se, all the way from spatial transcriptomics. There are bioluminescence detectors. There's a lot of spatial proteomics. Codex is one implementation that we've built. A lot of work on high content screening and bringing high content drug screening to small scale labs and actually giving these larger entities a run for their money. So first example I want to tell you about is Ebola. We were in Liberia for some time, and we've been ramping up Ebola diagnostics using our molecular platform that I don't have time to talk about today. But one of the key aspects was, I'm assuming some of you remember Monrovia. Does that name ring a bell when I say Monrovia? Yes, during the Ebola crisis, this was the center of all Ebola testing, and this is where much of Liberia's effort. This is LIBR. But now I'm wondering, do any of you know what a chimpanzee is doing in the middle of this photograph?
Guesses?
While you guess, I'm going to connect my power because I'm going to run out of power. What do you think a chimpanzee is doing in the middle of a Liberian research institute? Speak your mind.
There's one thought is about immunity.
Immunity, yeah, you're on the right direction. How have chimpanzees saved our lives? All of us, I mean, not just people in Liberia. Every one of us is thankful to these chimpanzees. Why?
Alonso says source of antigen from Peru.
Antigen, that's a good frame. Is there a disease that comes to mind?
Is there a disease that comes to mind? Joffrey, yeah.
There's SIV, which is considered like the precursor to HIV.
SIV, the precursor to
HIV. Yes. Every drug that was brought to the market around the time on HIV was tested on chimpanzees. All of those trials were run by the New York Blood Center. They were all run in Liberia. So the place that you just saw actually is a research center, but behind it are these massive cages, cages after cages, where chimpanzees were kept. NIH decides to cut down the funding for that. Nobody thought that chimpanzees live a long life, 60 plus years sometimes. And those chimpanzees that were in those sets of trials are actually still alive, and many of them were rounded and put on an island currently that's right outside Monrovia, and it's become an ecological crisis, kind of like Planet of Apes. They cannot be released out in the wild, but we have decided as a society that we're not going to care for them. And those chimpanzees currently are starving on an island. There is a couple of NGOs that have come about that once a while come and drop food on that island. Because of that program, it became clear that there was money to be made, and these researchers were buying chimpanzees. So across the country, still today, I mean, that program shut down 30, 40 years ago. Still today, people go into the forest, kill the mother, get the baby, bring them to a LIBR saying, oh, I heard you guys actually buy chimpanzees. And there is still this trade going on, and it's led to this massive crisis around the set of population. Why did I pause there from microscopy to chimpanzees? I just want to tell you that every action that we take has consequences, and we have to own it. And it kind of pains me a lot in which many of the advances that we move along and we actually forget what led to those advances. And we never pay back. We never pay back to the sets of what happened to that ecosystem. We never pay back to what happened to those animals. And we, of course, think about that, oh, all of this IP was generated, goes to certain sets of places and people, never returning back. And again, I think this has been on and on, is a classical framework that we've actually used. And it's important to remember that even in this perspective, we have to ask ourselves these sets of questions around when knowledge is shared or not shared. It wasn't just generated in vacuum. None of the knowledge is generated in vacuum. So if you're going to work, and actually a positive example of something like this is actually Institute Pasteur in Dakar itself. They were the first group to isolate yellow fever, and then they built a vaccine. And because they were the first group to isolate and built a vaccine around it, 90% of the entire budget of 1,000 people team in Dakar is actually funded sustainably by the selling yellow fever vaccine that all of us get. So, this is now another kind of a model in which people that really isolated that first virus, identified that for the first time, were actually empowered and engaged, and they were able to build something on top of that. So I think this is a choice that we make. And one of the things on our piece of the puzzle has always been around the idea that are we going to make the right kind of ethical choices? And again, this is something that nobody else will tell you. You will have to make those sets of choices. Your hand is not forced in these types of scenarios. Yes, you can cut corners and do what you need to do and get done with it. But frankly, is that the right choice to make? One of the things that bothered me was there is an Ebola trial that's been happening for a while for immunophenotyping of patients across Liberia, except none of the data is collected in Liberia. All the data gets shipped out, and all experiments happen in US labs. So we decided to build a platform. Now, I'm just giving you the modules, but I want you to think very broadly. There is a fluidic engine that we have built that allows us to do around 34 different reagents. Codex essentially is a process in which you can essentially wash and paint again and again and again. There is a clever kind of a DNA paint analogy that we've brought to this table, but you can now do 24 colors, so we can mark and label all kinds of immune cells. This is a PBMC mix. One of the other threads that we have done is in lifetime imaging. So many of these microscopes, I know many of you fight for microscope. This image is very special because this image is of the same organism in a function of its life. So this is C. elegans, and many of these instruments are used in live imaging in sets of scenarios. So this is sort of an application in which you're now watching that data set. Again, completely built open source, sent to a lab. They put certain layers and modules on it, and then they share those back to the community. And that leads to this massive growth of capabilities in assays. So I talked about Codex and immunophenotyping. Now this is lifetime imaging and incubation-based imaging. This is around 130 different worms that are growing continuously. Then we move to high content screening. This is another collaboration that happened in Uppsala in Sweden, and we realized that by combining simple open source robots with the microscopy, we can essentially do any high content screening. So these are 5 of these robots. Now this is scaling up with several sets of entities. This is the type of data set that comes out of it. So many of you are aware of cell painting. We basically designed it for cell painting. And to just give you a sense of what we can do with these instruments, that's a 96 well plate. I zoom in, that looks like one plate, and then that's the resolution that you're getting. And much of this is described in the paper. And to just give you the sense of giving entities a run for their money. So on the top here on the very right corner, I don't know if you can see my mouse. That's your Nikon TI2 field of view, and that's the squid field of view. Flat field of view for certain sets of pixels that we care about. And again, unlike black boxes, you can go and program as much as you want. We've done something very similar for optical pool screening. And one example that I want to give you is that these sets of instruments are now starting to grow as farms. So several of them put together, any number of open pipetting robots, some amount. So this is a farm of 10 sets of machines. We've built some of these farms as teaching labs. The first big farm is actually, we're building that in India as a way to show completely automated kind of event-driven microscopy. So you can see an incubator, you can see the sets of arms, all program in software that you drive what assay would you like to do. And again, do this in a manner that allows us to be able to build this capacity everywhere, not just driven by, oh, if you've raised $1 billion, you get to search, but build it bottom up, especially because now there is an incredible amount of things that are happening in the compute space, and we are going to massively increase the degree of automation and experimentation. So lots of startup companies have, and as a model of scaling up, I often do this in the lab. The first 1,000 instruments we built in the lab. So this is what my lab looked like at that time. We were shipping them to people around the world. We did the same thing with Foldscope, I'll mention in a second. But very recently, this became unsustainable. So we've started an entity in Menlo Park where we manufacture these sets of instruments. Many of the publications are here around the things that I talked about. And I'm going to switch and tell you 2 words about Foldscope and transition to Q&A. Actually, before I transition, I should just say a word about the ocean. So, the same analogy that you can think about in global health, you can apply that same challenging condition in what's happening in the ocean. So here is an example. All of you are aware of this. We all know this bottom curve. The top curve is the amount of carbon we put in our atmosphere. The bottom curve is the accumulated carbon. And the middle cyan curve right here is actually what the oceans absorb. So for the last 6 years, we've been obsessed over thinking about whether these plots are correct or not. Do we actually know, given X number of molecules that we emit, where do they go? And in the ocean specifically, where did they go? And again, going back to these sets of instruments and capabilities and taking them out to sea. So we just got back from the Arctic. We found the highest density bloom under ice. It's the highest reported biomass ever on the planet in water column, primarily hidden under ice where no light goes. And the only reason this happens is because the ice is quite thin. Also, there are fun visitors that come about. But the reason I just wanted to mention this is, again, using microscopy and event-driven microscopy, we were able to directly measure carbon flux in the ocean. And this has led to an 80 gigaton error in the current IPCC report. So that implies that we don't actually understand where all the carbon sinks on our planet are. It's the largest error that's been reported in the context of the oceans. Okay, I'll say a word about Foldscope. Planktoscope, a lot is online, so you can just go to this website, you can find the kind of data. This is the type of data sets that come out of it. It's flow-through imaging. It makes a lot of sense. This is the one-to-one map between the tools. One of these images is from a $100,000 instrument and another is from $1,000. And all of this data is actually from Planktoscope. Now, what's very interesting is because it's open source, anybody can build them. So any of you in the class can build it. The community is growing slowly. And we're starting to build a repository of these instruments. And one of the key is we keep adding capabilities. So one exciting part is now there are 2 instruments in the Bay Area that are completely in situ. So planktoscopes are not only on dry land, they are peering towards in the water. Okay, I will end with this image, a story that I don't think many people know. Many people know this story. This was the microscope that we made. The goal was $1, 1 micron resolution or submicron resolution. The only reason that's possible is a fat lens equation that we solved that allows us to optimize these systems. When I wrote this paper, we posted it on arXiv, and a gentleman that is well known wrote this tweet. I'm not going to name the gentleman, but I will read the tweet. I am a young professor. I'm excited about doing things in the world. And the person writes, a $1 origami microscope, question mark. Interesting, ... And I was stuck at that question mark. Why the hell would he add a question mark? Does he not believe what we have done? And we had just published the paper at that time. And it was sort of, this irked me so much that we realized the person has a point. Unless you scale an idea, you've not done it. I mean, we had written all the bill of materials. We had shown that this is possible. We had shown the manufacturing process. And at that time, I decided I'm going to ship a microscope to anybody in the world who asks for it. We shipped roughly around 70,000 microscopes in a period of 1 year. We turned the lab into a factory. And then we actually realized, what does it mean to share capacity? And that was an important aspect of this that has led to this full scope program per se. The instruments coupled to cell phones, they don't need cell phones. And effectively, one of the key notions is that it allows people to explore the natural world in its own context. So you understand the context. And much of that has been written about full scope per se, but one of the big things that we are struggling on and thinking about is it's taken us 10 years to reach 5 million kids. That's too slow. There is a billion people that live below, billion kids that live below $3 per day family earnings. And so you ask yourself, how long will it take us to reach a billion kids? If that takes you can do the math, that's still orders of magnitude, and that's still too far. And so one of the big things we've been thinking about is we're launching the stage 2 of this program, which is really targeting 100 million kids around the world. And we can't do that alone. And the way we do this is we pass the ownership and engagement to people around the world. So if any of you believe in community-driven science and biology, now you have the chance to build sets of programs to take the sets of technologies that you're developing in communities. I love this photograph, and I promise I'll end here. These are parents that are not sharing their microscope with their own kid. Those parents. Because you have to embody the science that you deeply care about, and you have to bring it to the communities that you care about, and then it spreads through osmosis. And so one of the important aspects of these sets of programs is that we need to be able to build a framework where anybody in the world can take scientific tools in completely new directions. And that's kind of what we've been excited about and fascinated by. But we can't do that alone. We can manufacture a microscope. We can't manufacture mentors. Most of the mentors are in this room, and if any of you have engaged with me, you probably already know this, that at the end of the day, it's many of you who have to drive and care about your own communities. So take these tools, put them in any way and form, but put them in use and bring them in hands of people, specifically kids, to see what they create with it. Because at the end, it's not the solutions that we create that will matter. Many a times our goal is to bring capabilities to people, and solutions are always driven by communities. So I'll end here. I'm hoping you all have time. I've intrigued you enough that you have some questions, and I have some time so I can hang out.
Amazing, Madhu. Manu, epic as always, and it's always exciting every year to see the advancements and the developments. There's kind of the core foundational work in the way that you always continue to grow it every year. So it's so inspiring. I personally have a handful of questions, but I know we've got a room full of folks here in person and also globally. So why don't we open it up? What folks have questions for you? Yes, go ahead, Cyrus.
Can you hear me or we are-
I'll repeat the question if you can't hear you. Yeah.
So the talk is fantastic. I really love the vision, so please convey that to him.
Yes.
So I really love this idea of science and bottom-up approach is really like fantastic and really, really inspiring.
Yes, very inspiring. Appreciates the bottom-up approach. Yeah. Yeah.
My question was mostly around, so of course it's wonderful to bring the technologies to the communities to allow them to make discoveries, but how do we ensure that those communities benefit? How do we ensure that
Yeah.
the key remains there? And
Yeah.
these novel things are discovered and protected and maintained and
Yeah, yeah.
those communities.
Great, great.
That's really important.
Okay, so the question, Mona, if you didn't quite hear, Cyrus, again, very inspired by the work. As you bring the tools to these communities, how do you ensure that the benefits remain in the communities? So things like IP, discoveries, and so on. So I'm sensing from Cyrus, which I also feel a lot, especially communities that are used to a lot of exploitation, right? So how do you ensure that the powers and agency and the benefits stay in those places?
Yeah, I mean, I think this is not a one-shot approach, and if you want to engage in a community, you have to understand, and then eventually you have to belong. And so this is not, oh, here is a list of tools. I mean, that happens naturally. We share what we do, but there is a much deeper engagement, and it all boils down to people. You have to find leaders in that community that then you are bringing on board. They have their own sets of views, they have their own sets of capabilities, they have their own sets of insights. And often enough, it's a tango that takes a long period of time. And, you know, there is a sense of trust you have to build in the community that you're trying to raise. It's very easy to break that trust, but very hard to build it or rebuild it back again. So it's very specific. I mean, for example, in Liberia, it's been very interesting for us because, many of the programs, the NIH sets of programs, there is almost no funding for it now. And our focus really has been on training the sets of individuals. Liberia doesn't have a PhD program, so we are starting a graduate program for the first time in many of these with partnerships. But one of the things that starts to challenge is this perspective that you have to build these relationships over long periods of time. And things happen slowly because at the end of the day, I mean, there are very classic data ethics that can be easily built on. So the reason we are launching the Octopi Diagnostics program with the way that we are launching is that the data ethics involves that the data belongs to the people in the communities that engage with us. So if you are an expert in leishmaniasis, you are building the app and you own that app, and a percentage of every time a leishmaniasis test is done on this platform, value comes back to you. And so it's about, just like we are all very creative in engineering solutions, we have to be equally creative in engineering the social context and engineering services that empower a larger group of people. So I think it's business as usual is not sufficient. And often enough, when we are transparent about it, many people have far better ideas than us on how to implement these types of services. But it's very case-based. It's very, very specific. With Foldscope, we focus on making sure that it's a pencil. You are given an empty plate. You get to do what you want. And in certain sense, we want you to have that discovery process. That's why Foldscope doesn't come with some experiments. We don't even tell people, oh, go look at onion cells. Onion cells is so dead. It's like so 1900. You should think about what comes about. Boogers and whatever is in your hand is what you should be thinking about. It's driven by people's, so we don't think of this in the context of textbooks. If you give somebody a pencil and start telling them you're only allowed to draw cars with it or write this type of poetry, how boring would that be? So you have to embody that in the programs that you build. Some amount of openness is there. And then it happens in a coordinated long-term fashion. I mean, some of the communities that we built them for 10 plus years.
Yeah, yeah. So Manu, again, I think part of what for me is so inspiring is you build a technology, you put it out there, and then there's usually some type of scalable community that is organized around that tool, right? And you've shown so many compelling examples and ways that you've replicated that model. And obviously, coming our lineage at the Media Lab is very much about scalable learning networks, right? Even this class right now, How to Grow, is a scalable learning network. So, one thing I'm curious about is you mentioned that each context is specific, which I agree. Again, it's sort of it's like helicopter science is the worst, right? You go in and then you drop off a thing and then you disappear. But a word that you mentioned that I think it's important to highlight is trust, right? And I think you saw Drew right after we were all at Asilomar, and he might have mentioned to you, the big theme for the next 50 years of biotech from that conference was trust. It wasn't anything about AI, it wasn't anything about a tool, it was about trust. So I'm wondering if you can comment, even in the context of specificity and context, what are principles that you've learned about how to scale a network effectively while maintaining and perhaps even amplifying like trust architecture?
Yeah, I mean, I think trust is a word that's used a lot and often very casually. You all know trust is built over long periods of time, and when resources are really limited and scarce, it's very difficult to maintain. And this is what I feel so sad about in what has happened in the last 3 months. This administration's removal of support has really shown the world that we are not trustworthy.
Yeah.
And frankly, no matter what, just for folks that are sitting in the US, no matter what your opinions are, what your beliefs are, because our government has done something like that, we have to bear that burden. We don't get to shy away from it. And it's sad reality of it. I go in and I introduce myself that I work in a lab in America, and that suddenly carries weight. So this is very, very complex. It's not so easy. It's not just your actions that drive, and you can't just protect your own network or you can't protect your own relationships. It's driven by history, it's driven by the past, being much more aware of that. There are certain sets of forces you can engineer around and certain sets of things that we can't. So I'm actually struggling significantly right now is what face do we have in this current day and scenario to be able to grow and continue the kind of work that I've believed in, anchored in, and I've actually explicitly thought about that maybe we need much more international anchoring in other partners. And, we work with many other partners, and I'm actively thinking about transitioning some of that work in partner organizations, which would be less influenced by a specific country's approach to this. So, it's something that you try to preserve, but it's difficult when all certain sets of circumstances around you are not aligned to your own value systems. And having said that, it's about sustainability. I also don't believe in charity. I mean, both Foldscope and Cephla are for-profit entities built on the goal of scale and bringing. They don't make money for anybody, but we actually try to build sustainability in all of those models. That is also an important thing, because what has happened in the past of just being completely dependent on charity made that a version of this model where we were not transferring technologies, we were not transferring capabilities. So a lot of our projects right now are not, the products are not what people use. The products are the capacity to make those objects. So in our diagnostics work, we're moving just completely in that direction. And then it brings trust, because then the dependence weans over time.
Yeah.
And I think this is something that should have happened in global health 50 years ago. It did not happen. And whatever disruption is happening is also an opportunity to think like that.
Yeah, that's great. Yeah, Vincent's.
I kind of pushing in on that. Why do you think that there is not more challenging, or particularly historic cases, more traditional approach of having kind of this kind of garbage? Not all these funds and not trying to come out with cheap solutions, but instead dependence. And do you think that based on what others are doing that we're seeing now over the past 3 months more movement away from that?
Were you able to hear that, Anu?
No, you have
No,
to
so
repeat.
since I'm not sure, I'm actually not sure I understood the question. Say the first the core part again.
Your technology has been really breakthrough technology, but
Yeah.
it's very expensive to do before. So why have not more people kind of taken this approach to
Ah. Okay.
give empowered people?
So in a way, why has frugal science not happened earlier?
Yeah.
Yeah.
Why are not more people jumping on the train?
Yeah, and so I guess maybe it's a question of incredulity. Why have this not happened earlier, and why are not people more adopting this approach of low cost distributed open source tools?
That's a question that other people should answer. I don't have to answer. I do what I can, and we talk about it. I think it's a perception problem. Science used to happen. The origin of science arise from you have a problem, you care about tackling it with what you have. We've created kind of this perception around an idea that, oh, science happens when you have all of these things and everything is perfect. And most scientists were tool makers. But we have stripped away the capacity to make tools. We have siloed people in ways and forms where only a few people will describe themselves as tool makers. And often enough, that kind of creates sense of barriers, and we fight those barriers. We bring sets of tools. And again, of course, complexity of sets of ideas does require teams to work together in some sense. But as individuals, you should all strive towards being a holistic scientist. That at the end of the day, you should have the capacity to understand the math and the physics behind an idea, understand the history of biological complexity that's embedded in the system that you're working in, have the capacity to deeply understand and actually build the key tools that are needed. And it just requires more resilience and more time. Acceleration of science does the opposite in many ways. You want to just completely quickly come to an answer without deeply understanding what that answer actually means. So these shortcuts have made people feel that, oh, we can arrive at these sets of things quickly, and then resources drive to a certain extent the speed at which who arrives where. So I would argue that frugal science has existed forever. Raman knew how to do frugal science. He didn't depend on it. He didn't ask anybody if you're going to build me this type of a spectroscopy tool. He just went and built it. And frankly, this is nothing new. It's important to understand that scaling arises from making sure that the work that you do, you ensure that other people will be able to build upon that work and do more with it. Because our time is fundamentally finite. As scientists, no matter how brilliant you are, you're only here on this planet for a finite amount of time. The most important legacy that you will leave behind is the work that you leave behind if others have built on top of it. So if you make that your goal, that I evaluate not by citations, not by which journal that you publish your paper, by the number of people that truly actually built upon your work, and we literally hold people's hand to make sure that that happens. So it's a very active engagement process. It's not a passive process. You don't toss projects and make a website and hope this would happen. I teach a class called Frugal Science. Any of you can take that class. It's, again, a global class. Any of you can take on and talk to other people about frugal science. You can teach them tricks of the trade. You know, we can all spend time thinking about it. Just I find the idea that cost and scale are deeply connected, so it's very important for us to actually consider and think about it. It's important to understand that this is frugal science. I didn't use some other word for it. I said science. It still take us years. I mean, I showed you Inkwell in less than 30 seconds. It took us a year and a half to build that thing. Now, in an hour, you sitting there, if I send you the file, can make that tool completely for free. But it took an incredible amount of time, energy, and effort, and I valued it. And many a times, most people might not value it. So, in some sense, it's frugal science because you still have to deeply engage in and re-question everything that you know. So it doesn't happen in my spare time. This is what I do. And if you can do that, then you will build the kinds of solutions that actually scale. So it's not an afterthought. It's something that we choose from day one.
Yeah, beautiful. Maybe one more question. Yeah, Shrika, go ahead.
Sorry, I guess this isn't meant to downplay malaria at all, but you presented that it was like higher, but at the same time, we also like with some of the frugal science schools, it seems like it's easier to test for like a lot of these conditions. I was wondering how much of that increase, like not just malaria, but in general, you attribute to actual like increase, and then how much of that could be like just accessibility testing.
You mean the
malaria?
Yeah.
Yeah, for
Yeah, no,
malaria.
it's increasing. It's not our capacity to test is actually decreasing, unfortunately. The annual budget fluctuates, but it's been flat. So it's not as if we're doing more diagnostics. This is not the COVID world where we had tremendous amount of resources being poured in. Nobody cares. So the amount of money that's gone in diagnostics, every year the number of tests that we do has remained flat, but the number of positive tests is increasing. And we have an understanding. I mean, ecosystems change. Why do we believe that a disease that's so complex should remain flat? When explicitly, these are adaptive systems. Remember, these are living systems that know how to evade. So, if it's the Red Queen hypothesis, if you keep running, you remain where you are. You have to run much, much faster to eliminate anything.
Manu, you've been so generous with your time. There's a couple of other questions in the chat, but one very practical one. Can people still sign up for your class, the frugal science class? Is that ongoing now? When is it happening?
Yeah, I think we're halfway currently, but if people want to join in, we are about to start building projects. So just go to frugalscience.org or send me a message somehow. And if it turns out that you can quickly join a team, that should still be okay. But we also record all the lectures, and at some point of time, we should tag team and do the two community collation.
Oh, that would be awesome. We
figure that out
absolutely
at some
should.
point.
Yeah, that'd be epic, Manu. I have just maybe like one, it's a combined question. I'm gonna combine three questions into one question. It's a technical question. So at the very beginning of your talk, you showed some microscopy images and you said, hey, you can look at these genetic disorders just through microscopy. Actually, I'm not sure you circled all the way back, so I just wanted to raise that. But connected to that question, I have two adjacent questions. You mentioned several times about this AI engine that's driving your robotics, and I know it's in a talk like this you're covering so much so you don't have a chance to go into it. But again, it'd be I think many students myself are curious about what that engine is. And then the third related question, as you've been scaling your robotics now to these farms, right? One thing that struck me was kind of, you've talked a little bit about black boxes and then open source, right? So you open source, you can go build upon it, do other things, but then, as you're engaging with more and more sophisticated automation and robotics, is there now a tension between the black box and the open source? So anyways, I put all of those three out there, and
I'll
feel free to
answer
answer.
them backwards.
Okay, great.
Just so that I remember the most. The tension sometimes is you want stuff to work. That's the most important criteria in science. And you want stuff to work quickly.
Yeah.
And the reason we manufacture them is because all the layouts and the plans are there. But to manufacture a stage that will have nanometer scale precision, every single time for thousands of cycles. Some of our microscopes, we don't turn them off for 6 months continuously. The
Wow.
stage is continuously moving. The data set that we are publishing with Uppsala in Sweden, the stage is continuously moving for 6 months at that precision. So that requires this deep rigor in manufacturing. And so we've had to build that capacity. And once we built that capacity, we were able to do those functions. So certain sets of core functions are driven on foundations that need to bring robustness. The reason we can do so many applications is because our platform is the first platform that's completely open. And I don't know why nobody's done that in microscopy. But the moment we were able to show that we can do highest quality data in the open, other people started building layers. And so we started building collaborations. So Codex is a collaboration with a group at Stanford. Raman was another collaboration. OPS is another collaboration. Expansion microscopy is another collaboration. So we were able to build little mini communities around this. And then once those modules are built as a community, then we again bring robustness to it. Because at the end of the day, we have to build products. I have a very product oriented mentality that if I ship something to someone, it must work.
Yeah.
And there's no compensation around it. It must work out of the box. But we leave all the APIs and everything open. So when you have a new idea, build anything on top. And we will only engage with you in a meaningful way if you believe in our philosophy of keeping things open. Otherwise, you can do whatever you want with it. It's there. But for us to meaningfully engage, so this is how we reciprocate and we force people to reciprocate, that they're excited about what they're getting, they're excited about building new capabilities, but they also have to buy in on the vision that many more other people will be able to do and build upon what they did. So anybody can build a module. If any of you want to build a temperature control module for our instruments, we'll help you, we'll support it, but we also want to make sure that you try to keep it in the open. And you can also still build a closed version of it, but then the engagement is not so direct because we feel it's a certain kind of people we want to invest in.
Got it.
Software scales very quickly. It is absurd to say that automation software is not open. I mean, it just that does makes no sense to me. Why would you ever invest in something that you cannot modify? So talk to your PIs, tell them not to do it. Because at the end of the day, you win in short term, you don't win in the long term. You don't actually understand what's behind the radar. We get all of these data and plots that auto generate. We don't actually understand what happened. So if you really are trying to do science in which you're trying to build certain sets of capabilities, especially new assays, you never do everything exactly that somebody else described. So modification is very critical. And so the least effort is on the software layer. And now with many of these AI tools writing that software, it's become really fun for us to see how people will modify the entire thing. And we have an internet connection into our machines, so we can log into our machine. If somebody has crashed it completely, we can bring it back alive, reflash the whole thing. So we do all kinds of tricks to make sure that people can just mess around and play with. Now, another layer associated with this, now the next question you ask is the AI engine. There's no one AI engine. It's been for specific problems. For malaria, we built an engine. Now, you have to remember, for malaria, it's a very different requirement than all the research tools because for malaria, I'm very power limited. Most of those primary health centers are running on solar panels, and I need to do it in real time. Unless a community health worker can tell me exactly what the disease look like in real time, it's of no use because people can't find the other people. So there's a little bit of a tension. So the AI engine that we have built is very power sensitive to that. While there is another version that we have built, which is really much more about some of our open kind of tools in the science world. And in that, we have ways of, I mean, there was one tool that we just built in which it's an event-driven tool. It's integrated with ChatGPT. You write certain sets of instructions. It writes code around it. That's based on LifeSci, which is another entity out of KTH. But I think the idea is there is no one universal engine. It's really actually dependent on what you're trying to do. For some of the other tools, we care about speed and we are very data limited. We generate so much data that we can't even store it. And so then it becomes this problem of, oh, making sure that we are actually doing certain sets of things that are much more precise. So right now it's in flux. We have not released any of the AI engines yet. We have worked with certain partners, so we are still in the prototyping phase. The first one we will release will be in the Ashoka University in India. And from there onwards, that'll have the first stable version that anybody can play with. And then the third question was on Raman. I think I just wanted to mention label-free imaging has a very powerful capacity. It turned out the reason we can detect many of these antibiotic resistance genes is because many of them operate on the cell membrane. And Raman is what is sensitive to the group of molecules that exist on the membrane, because it's so this one happens to have a gold nanorods that kind of emit this evanescent wave. Much of the amplification for the Raman signal is coming from the membrane. And initially, I wasn't sure if we will see it, but currently from the data, we can tell it's coming because the composition of the membrane has changed somehow. That's and again, it would not work for completely other type of resistance, but this particular one works because many of them are very specific to modifying membrane biology. That's our intuition. But again, with Raman, the challenge is you don't get to verify it because there's a billion molecules on it. We just get a spectra and we just train a machine.
Yeah.
And we get these very robust results. So we're expanding it, but it's very difficult to verify to say which molecule led to that most learned feature.
Got
We
it.
do some of that work in controlled environments, but these are clinical samples. These are clinical
Yeah.
replicates. So it's much harder.
Manu, you've been so generous with your time. We're just about at the hour, so we'll wrap up there. Everyone, can we just give another huge round of applause and thanks to Manu for time.
Bye, everyone. And I'm happy.
Thank you
to
so
engage.
much again, Manu. I think you're going to have a whole bunch of rogue students joining your class now. There's the whole discussion is how do we join the class? So you're going to get a lot, I think. So thank you so much again,
About
Manu.
the class, I can just say this. I'm sure David might have said something like that. Our classes are not spectator sports, they're contact sports. So that means you should be ready for contact and ready to actually engage in projects. There is a peripheral side of it where people just want to watch it from the side. That happens with all the lectures that we post online. But anybody who takes the class, get ready for contact.
We love that. How to grow is a contact sport too. So they're all ready. So all right. Thank you so much, Manu. Take care. See you later, my friend. Bye-bye. All right, everyone. So we are I had a whole lecture, but I think Manu's a rare gem for us to come and connect. So I can share some of the work I was going to present potentially next week during recitation. But for now, why don't we wrap up there? One other quick thing to show before you all leave. So just one other quick note. So this was shared previously, but I wanna highlight this very quickly. Next week, you all are gonna have an optional lab. Okay, obviously you have full-on final projects going on, so focus on that. But Ren, who's a PhD student in biological engineering and also a co-advisee of mine, has got a really wonderful biomaterials workshop. This is optional, so you don't have to do it. But if you are interested in working with mycelium, making some artifacts, Ren is receiving molds right now. This date is inaccurate. Ren actually mentioned to me Monday night. Okay, so if you can get materials to Ren in terms of a mold that you might be interested in making by next Monday, you can actually make a mycelium object connected to that. All right, so just know that. Yeah, please go ahead.
Could I get a raise of hands of who would be interested in this? Because we're trying to figure out how many we need to get. Okay, so that seems like around 8 or 9 hands. So to make the molds, there's a couple ways. You can either get like any CAD software. So for example, Fusion, SolidWorks, whatnot. and
3D
then
printing.
then, yeah,
You 3D print the molds. That's
but to like
basically.
design it, you also would.
Is Ren 3D printing it or that we asked?
Sorry, 3D printing it. Yeah.
Oh, okay,
Yeah,
okay,
yeah,
all right.
yeah.
Oh,
But
great.
We just need to know like as soon as possible if you're interested, just so we can order the correct amount of kits and then get them. So
I thought you already had the kits.
we have some of the stuff. We're still waiting on a few more. We
Okay,
talked about this,
okay.
yeah.
All right, so then just keep your hand raised if you're interested in participating in this. So this is 1, 2, 3, 4, 5, 6, 7, 8. Okay, great. Yeah, and Ren's gonna have some of her own molds, but if you want to make your own, which I recommend you do, if you want to have some cool mushroom artifact that you can bring on with you, a mycelium artifact, then what's the deadline to send you guys prints?
As soon as possible, like preferably before like next Wednesday.
Oh, well, of course, we're next Wednesday, but this week is if this week isn't printed
That's
in
fine.
time.
That's
Okay, all right. So send your molds over this week if you want to get your stuff printed for this. So, all right, everyone. Thank you all so much. We'll see you to recitation tomorrow. Final project presentation prep. So, enjoy.
Wait, is there a timeline?